before we begin for everyone to get into the room. We will start in a couple minutes. Okay, to those of you who just joined us, we're just giving a couple more minutes before we begin for everyone to come in. Still have some people still joining the room, and we will start shortly. Thank you, guys. All right, I think we're just about ready to get started. Good afternoon, everyone, and thank you for joining us for our webinar on harmonic modeling and analysis. My name is Wes Dyson with AMSC's marketing team. Before I introduce you to our presenter, I'd like to just call attention to the chat panel over there on the right-hand side. It looks like some of you have already found it. That's where you'll be able to communicate with us during the webinar. And also ask any questions during it. I'll go ahead and put my email address in there now, just so you can see that. And if you experience any technical issues during it, you can go ahead and email me. It's the same email address I sent the reminder for the webinar this morning. If you experience any technical issues, I'll be able to help you with that. For your questions, we also have one of our inside sales managers here to answer any questions specific to the equipment itself. But if you have any questions for Chris, our presenter, while he's talking, he'll be doing some specific question and answer periods. I think towards the middle and then again at the end, if you want to hold your questions till then. And if for any reason your question isn't able to be answered or we don't see it or anything like that, feel free to email me your question and I'll make sure someone answers it for you. And without further ado, I'm going to go ahead and introduce our presenter, Chris Duffy. He's a senior technical staff engineer here at American Superconductor and a licensed professional engineer in Oregon. Chris joined AMSC's network planning team in 2022, performing system analysis for the DVAR and DVAR VVO StatComs, Neeltran rectifiers, and NEPSI harmonic filter product lines. I forgot to mention as well, the inside sales manager that is with us is Alex Stechik, and we appreciate him being here with us as well. And without further ado, I'll go ahead and pass it along to Chris.
All right, let's just do a quick check. Can you hear me?
I can hear you fine.
All right, that's great. Well, good morning, everyone. We have a lot of material to cover, and so I'm going to dive right in to harmonic modeling and analysis. So let's get started. Now, obviously, we have to have our legal notice. not guaranteeing anything in the presentation. It's kind of interesting. It's the standard thing we all do as consultants, but I won't read all this through. We'll just skip by this quick, but you know it's there. So the purpose of this webinar is to educate and share the technical knowledge that we have on harmonic systems and modeling with our attendees. We're going to cover the general aspects of harmonic modeling to establish a foundation for not only proper modeling and analysis, but also for just understanding what you're getting out of your harmonic tools that you're using. So obviously for simulating distortion conditions in the power systems that you're modeling. And once we have that foundation, then harmonic mitigation methods can be simulated and benchmarked, vetted before we do any procurement or installation. So let's dive right into our theory. Now, every single presentation on modeling or harmonics or any type of power system analysis needs some type of an upfront theory review, just like any college class that you would take. And so I'm going to do the same thing here. We're going to look at 4 key topics: superposition and its importance, Fourier analysis. I think we all understand the reason why that's needed. Phasors, though a lot of us probably had phasors in college and using complex numbers, I'm going to touch on it briefly just because I think it's really key and important to understand the foundation of why we can also use that for harmonic analysis. And then we're going to look at some AC system analysis methods. Superposition. So in our context of physics and electrical engineering, superposition is an absolute necessity for harmonic analysis and study. It's one of the most overassumed principles, and it's a principle that manifests constantly in nature. On the humorous side, for our reference frame, superposition is not related to quantum physics or Schrodinger's cat, and it's not a placement of one thing above or on top of another. What we're talking about is the physics portion of superposition, where we're needing it for how we analyze and break up systems. Now, superposition naturally occurs in visible electromagnetic radiation or light. Using a prism, we can extract, we know this, right? We can extract the individual frequencies from white light, and inversely, we can blend specific colors of light and create an unlimited number of colors. Without superposition, our eyes would not be able to distinguish these differences in light. We would not be able to see color. So a nice slide here just showing that the frequencies are broken out into individual colors, each with a unique frequency, coming all from a beam of white light, which is really a totalized beam of many, many frequencies that exist in white light. It's not exactly purely white because we know that our sun has particular elements within it. And so there are some places, where it specifically has elements that are showing up in the white light. But for the most part, we can consider it to be almost like white noise, where it contains all frequencies. In sound, superposition also naturally occurs in sound pressure waves. Using audio filters, we can separate out particular bands for EQing or musicality, or individual frequencies for devices that perform noise suppression. Inversely, we can take specific frequencies and add them together to produce musical sounds, and that's synthesis and synthesizers. Without superposition, our ears would not be able to distinguish differences in sound frequencies, and we would really not be able to hear, especially the type of hearing when we talk about hear, and that is to be able to distinguish one thing from the other. Here's a good example where you can see this sound wave, the sound capture at the top of this picture. It's got a broad range of additive sound frequencies that contribute to both a fundamental note and a host of overtones that create what we call timbre. And this is how we can distinguish, for instance, between a violin and a cello. Now, superposition is also used to analyze electrical circuits with multiple sources. And if you remember any of those who had the college background, if you remember this, you remember doing linear network analysis, you remember taking circuits and with multiple sources and actually calculating what the net result was at a point. I'm not going to read this complete definition out of Terman's Radio Engineer's Handbook, but the key thing is that it's stating is that at any point in an electrical network, you can calculate the resultant voltage or current at one point due to multiple sources by doing an analysis multiple times, each one with each individual source. And that would be like this. We have a circuit on the left. It's got two voltage sources, and we want to analyze and determine what is the voltage at V3. To do that, if you remember your circuit analysis, we go to the first source that's on the top here on the right-hand side. We short the voltage source that was V2, and then we perform a little parallel series combination of resistors, and we can calculate the current I13. Similarly, we can do voltage source 2, and then we can calculate current I23. We put them into this quick equation. We can calculate the voltage V3. Again, this is kind of simplistic, but it's trying to bring home a point. And that point is that we use individual computations independent of the two sources, literally working independent, calculate these two currents, and then can get a net result at V3. So superposition is also completely dependent upon having what's called a linear network. I'd like to read this in, the full text here, just write out loud for us. So a network is made up of resistances, inductances, capacitance, and mutual inductances connected together in some manner. These values are termed network constants or parameters. When these parameters are constant and independent of the current going through them, the network is said to be linear. For all of the AC network analysis that we perform typically as engineers, what we'll find is that we're always assuming that the network is linear. We may not realize it, and we may have been taught, to do these calculations, and this is how you perform the analysis, but in reality, to do them, you are assuming that the network is indeed linear. So, superposition, using analog or digital methods, we can literally break down a complex waveform into many single frequency parts because they're superimposed on top of each other. And similarly, we can take many single frequency parts and add them to reconstruct a complex waveform. The Fourier series that we're going to discuss next is a natural mathematical expression of superposition, where each frequency acts independently of the other, but sums to create a net resultant waveform. And this will play out directly into the methods that we're going to discuss on how we do harmonic modeling. So, superposition thus allows us to analyze each frequency independently, sum the results to achieve totalized result metrics, like total harmonic distortion, and a number of these other values that we look at in harmonics. It allows us to create efficient numerical methods to be able to perform the type of analyses that we want to do, especially on large-scale systems. And it allows us to perform highly accurate real and reactive power measurements, and finally, to perform equipment designs to address excessive or unwanted distortion. So let's jump now directly into the Fourier analysis portion of this. And that is Mr. Fourier here, shown on the left, Joseph Fourier. So the Fourier series that actually bears his name, these methods were used by a number of his contemporaries at the same time. So it's interesting that we call it the Fourier series, and he actually used it for heat transfer analysis, not for anything electrical. Interestingly, and you can go on Wikipedia and other online sources, you can find a lot of interesting things about Fourier, but I thought I'd bring a couple to the table, and that is, he was a friend and a prefect, a government official, for Napoleon in southern France. And he befriended Champollion, and probably in French you would pronounce that differently, I'm certain. And that person was the decipherer of the Rosetta Stone. So often in history, we find that there are a lot of people who were contemporaries and knew each other in the day and were related and were friends. And if you're familiar with the Rosetta Stone, that is that large black stone that has multiple languages and was a key for helping to decipher a lot of the ancient languages. He is one of 72 names inscribed on the Eiffel Tower. Interesting facts. So Fourier series and Fourier transforms have been used and adapted for a limitless, you almost can't count the number of scientific and engineering applications where the Fourier series and Fourier transform have been used. One of the key reasons why, and I've been hitting constantly, and I'll probably continue to hit on, is that the Fourier series, like I said, is a natural expression of nature. It actually of how light works, of how electromagnetic waves add together, electrical waves add together, how sound waves add together. And so because of that, these things are just, the number of applications are just expansive. So Fourier analysis is essential also for measuring harmonic conditions in electrical power systems. Most of us know this. If we want to take a waveform, get the harmonic content out of it, we have to use a form of Fourier analysis to extract those frequencies. Now, as noted earlier, the Fourier series is that literal mathematic expression of superposition. And Fourier methods are so widely used, we have even developed optimized algorithmic methods for computation to make them much, much faster. And we'll briefly mention that, and that's called the fast Fourier transform. Now, Fourier series is based on fundamental frequency and multiples of that fundamental frequency that we call harmonics. And here are the two common forms. We're not going to dive a bunch into this, but again, we're looking at the surface, just trying to get some foundation laid in front of us so that we can fall back on this if we ever need to do any advanced analysis or computations or some theoretical work on it. The one that I'm going to be spending most of my time on addressing would be the exponential form. And that is very important to note, the exponential form, because it gives us both magnitude and phase for our Fourier components. Now, it's really, I'm going to read this last point. It's almost counterintuitive to think that a smooth sine wave, several of them added together, can create a square wave with rather sharp waveform edges. But it is indeed completely true. And if we look over here on the left, I did this in Excel. All I did was create a fundamental waveform with 128 points, and then the third harmonic, the fifth harmonic, and the seventh, with the third being 1/3 of the fundamental, 1/5 of the fundamental, the seventh is 1/7 of the fundamental. And you can see that if you add these up together, point by point, you're already approximating a square wave, which is adding the third harmonic. And then you add the fifth, you add the seventh, and now you add everything all the way up through the 25th, and you get this, and finally all the way up to the 49th. And boy, we're getting really, really close to a square wave. So interestingly, if you remember any work back in college where you were looking at calculating the Fourier coefficients, which are these AN, BN, CN values, you remember that you had to apply some integral calculus and methods to calculate them. And it turns out that for a square wave, they turn out to be a very simple series of 1/3, 1/5, 1/7, whatever harmonic number you're at, that is it. Your magnitude of your coefficient is 1/3, 1/5, 1/7. So the example shows that, yes, adding of harmonically related sine waves can literally create another waveform that literally resembles a square wave, and will be. If you kept going all the way up to the 100th, the 200th harmonic, you would basically form an exact square wave. But by the time we reach the 49th, it's pretty apparent, right? It's there. And each of those individual sine wave waveforms were added together to construct that waveform. This is also an example of additive synthesis, and this is exactly what some synthesizers will do to produce a fundamental note with overtones, right? The third, fourth, fifth, sixth, seventh harmonic. In this example, because this waveform is symmetrical about the zero axis, you only have odd harmonics, 3, 5, 7, etc. Okay, now in the Fourier, in the time domain and the frequency domain and how they relate to each other, the all the work and the theory done to help us out that were done hundreds of years ago previously for us is all kind of summarized in the Fourier transform. It's a continuous form equation. And so it's a mathematical relationship that helps you take functions that are equations, sine of this, of 2x squared, 3x squared, whatever, some form of an equation, and then process it to generate what's called the Fourier transform in the frequency domain. And so that would be x of omega would be the resulting equation where omega, if you can remember, is always 2 pi f, right? 2 pi times the frequency in hertz. And it's equal to this integral. And in looking at this, the key part that I want you to see is just that the real-time function, whatever it happens to be, whether it's a waveform for a power system, whether it's an audio waveform, whatever this happens to be, is just multiplied by this value, e to the minus j omega t, and we're going to look at that in just a second. And you perform this integration. If you remember integration, it's just a summation where dt happens to be very small, and you just accumulate. So it's an area under a curve. Now, there's another identity that we could spend a lot of time trying to figure out how to prove, but let's just use it as a tool here. And e to the minus j omega t, which is here in this equation, happens to be, by Euler's identity, cosine omega t minus j sine omega t. If we substitute that into the Fourier transform, we get this, which x of t times cosine and j sine. And then if we realize that with integration methods, if we have an add or a subtract here, we can break it into two separate integrals. So we have an integral of this part and an integral of that part. And if you know complex numbers and you remember vectors and complex numbers, this left-hand part is the real part. And this right-hand part, once you calculate it, is the imaginary part of the complex number. And we can show that here in this form. So x of omega is actually a real part of x of omega plus j imaginary part of x of omega. Likewise, we can calculate magnitude and phase. Square root of the sum of the squares is the magnitude, and the arctangent of one or the other will give you the phase of this. And this is really important to realize because in Fourier analysis, it will yield both magnitude and phase of a waveform's fundamental and harmonic content. So every frequency that we analyze out of a waveform we're going to be able to obtain from it, whatever that waveform is, we're going to be able to pull out not only what the coefficient or the magnitude of that waveform is, but we're going to be able to extract the phase of it as well by using the Fourier transform. Now, the way I like to look at this, to move from that integral into a form that is more discrete. In other words, I can have a table of numbers, right? And in that table of numbers, I can process them by substituting a summation sign for the integral and doing just Euler integration technique. Let's look at 60 hertz. So if we have 60 hertz, we can say that x of 2 pi 60 is equal to this integral where we have the cosine of a specific frequency and the sine of a specific frequency times our function x of t. Well, let's convert this into a more discrete form. And if you go through the work and the dotting of i's and t's on this, you'll discover that this, whatever the x, whatever it is at, and this, this frequency domain value at 60 hertz will be the square root of 2 over 128. By the way, realizing that I want to get away from peak values and I want to look at RMS because it's more meaningful to all of us. The summation 1 to 128 x of n, which is our function over time times the cosine function. And over here on the j side, it's the exact same thing with the sine. That basically is in essence the same as taking our time waveform, whatever it is, multiplying it by a cosine function, taking the same time waveform, multiplying it by a sine function. This will give us real and imaginary parts of that frequency that we're trying to extract. And we calculate the magnitude as the square root of the sum of the squares and the phase as arctangent of B over A. All right. And I actually have an example for you to show that this is actually true. I mean, it's kind of interesting to say it, but it's more interesting to kind of prove it in a spreadsheet, right? So what I have here for you is a waveform that I have constructed. 60, I've given it a magnitude, a frequency, a magnitude, and an angle. And if you take a look at this, you'll see that that's what this is. I can change the voltage to 120. It's going to raise the thing. If I put it on 100. If I add a different additional waveform to it, like the fifth harmonic, then I'll put the 10 volts of fifth harmonic on, and you'll see that it will indeed create a polarized waveform. What I've done here is I've taken the waveform, I've created a cosine function at 60 hertz, that's all this is, and I multiply these two columns together. I do the same thing with the waveform and the sine function here, and I get the waveform times the sine, and I generate the sum, you can see it in the equation, sum of this column, sum of this column, and here I have calculated the real and the imaginary part. I take the square root of this, and I do this, 128 division, square root of 2 factor, and lo and behold, I have the magnitude extracted out of this waveform. So I can add 100 volts of fifth harmonic content, and I can still pull out 100 volts of fundamental at minus 90 degrees. You see, if I change this to 0, it extracts 100 at angle 0. So here you have a simple spreadsheet where all you have to do is multiply your waveform by sine cosine, sum it, divide it by a couple factors, and now you can actually fully extract that frequency out. And I have another example here where I've taken a real waveform of a rectifier system, where these are the actual current waveforms. I've copied one of these three phases. You can choose here 1, 2, or 3. And if we go back to 1, and I say, what is it? What is the fundamental component of this? And it happens to be 1153 amps at minus 111 degrees. And if I say, give me the fifth harmonic, which is 300 hertz, it'll pull out that the magnitude is 234 amps at minus 12. So you could do this for all 50 harmonics across your spreadsheet if you wanted, and you would have your own tool for basically extracting harmonic information out of a waveform. So returning to our presentation. How do we do it fast and really efficient? That's the fast Fourier transform. It literally is the exact same method that I just showed you, except it's computationally efficient. And what it does is it reduces duplicate computations and duplicate calculations of sine and cosine so that you can save time and computational energy. And this was created, the first major breakthrough in the FFT was by James Cooley and John Tukey. This was a number of years ago. And their butterfly algorithm reduces the number of computations by a factor of over 200 so that you can do a Fourier transform and be a lot more efficient with it. Okay, phasors. Now, we're turning the corner. We just had some background on, and I threw a lot at you, but now I'm going to throw a little more, and let's jump into the phasors so that we can have, again, that good foundation for why we're doing phasor analysis. So Charles Proteus Steinmetz, I don't know if any of you know who he is. He's basically one of the most famous electrical engineers who ever lived. And in his day, he was actually more famous than Tesla. Tesla has this name that has carried through the time because he was such a showman. And indeed, he was a brilliant man too. I'm not saying he wasn't, but just so you know that a lot of the things that we take for granted now in AC power systems were generated and developed by Steinmetz. He pioneered the concept of phasors for analysis of AC system. He had over 100 patents, worked out of Schenectady, New York, which is where I had my first job in Schenectady. And there's a city park, Steinmetz Park, named in his honor there. And his house still stands today in the GE plot. So phasors are related to consistent and repeating sinusoidal waveforms. And that is, we're going to assume that they're not moving around for this analysis. In other words, we're going to assume first that they're sitting still, and that's what we choose as our basis for this. We're not having any subtransients within that waveform. We're thinking of only, for instance, 60 hertz or 50 hertz or 400 or 25, whatever frequency you're analyzing. We're going to assume that it's constantly repeating. And before Steinmetz, AC systems were being modeled with all types of extensive use of calculus because no one had developed this analysis method yet. So Steinmetz discovered that this consistently repeating sine wave of voltage and current can be represented by a complex number with magnitude and phase. The phasor. The phasor is nothing but a complex number. This also held true for the effective, quote, impedance of a network. The impedance didn't exist at this point yet before Steinmetz coming up with this stuff. So basically what was developed was a complete methodology for AC system analysis. And from this, we discovered that we can use algebra instead of calculus now for doing AC power system analysis. And that analysis with complex numbers or phasors was born. So if we have a waveform that's constant and we pull and we say, well, all the other cycles are the same, so let's only analyze one. Let's just look at one. So if we look at one of these waveforms, we see that we have a peak on the voltage. And what we can do is we can start working in the realm of phase instead of time. This waveform repeats on time forever. But if we look at the waveform, we realize, yes, we can go from 0 to 360 degrees, shown here on the bottom axis, or 0 to 2 pi in radians. So we're going to shift from a time frame into a phase frame. All right, so the AC waveform we're saying now can be represented by a phasor or complex number with magnitude and angle. I'm showing that example here. Notice this is maybe hard to see on the slides, but this is a bold V. So anything that's bold, I'm calling a vector or a complex number. Instead of the peak of the sine wave, to foster numerically correct power calculations, we decide to use RMS. And we could go into a whole explanation on RMS as well, but let's just understand that this is typically how we do it in AC power. We say that the vector is forward from the RMS value for that single sine wave at an angle theta. And as most of us know, RMS voltage is equal to the peak over the square root of 2. And that would look like this. So here we have a vector. It's a magnitude of 70.7 RMS, which is 100 volts peak, and it's lagging 60 degrees, which shows that the waveform is back from the 0.60 degrees. RMS is shown here at the 70.7 level, just to give you a reference point with how the RMS and the peak compare with each other. Now, further analysis showed that for a resistance, a pure resistance, Steinmetz determined that, hey, resistance is, you get no phase difference between the voltage and the current. And so the resistance can be modeled as whatever the resistance is at the frequency that you're working at, which for 60 hertz, RF is a little bit greater than the DC value. And we can find this in by measurement, or we can do it in lookup tables. Further analysis showed that current flowing through a purely inductive component lags the applied voltage by 90 degrees. So here we have this, it's lagging by 90 degrees. And he also determined that the reactive part of that impedance was found to be 2 pi FL at an angle of 90 degrees. In terms of a complex number, we can represent that as J 2 pi FL. Similar for a capacitor, he found that the current was leading by 90 degrees, and he determined also that the magnitude of that reactive part of the impedance was 1 over 2 pi FC, which means the reactive impedance is minus J 1 over 2 pi FC. So we can, noticing that XL and X sub C are in quadrature with each other, with the resistance 90 degrees displaced, we can form a general complex value of impedance in Ohm's law. Z equals R plus JX. A lot of us are very familiar with this. So for resistors, inductors, and capacitors, we have these forms. We have the resistance normally If it's pure resistance, we ignore any inductance, and it's just the resistance at the frequency. Here, for the inductance, RL plus JX sub L, for a capacitor, it would be RC minus JX sub C. This plus and minus are very important when we do harmonic calculations and when we get into the harmonic realm. So phasors, some observations. X sub L and X sub C are 180 degrees apart on the complex plane over on the right-hand side. You want to plot minus JX sub C, it's down. JXL is up. R is on the horizontal line of the complex plane. X sub L increases linear with frequency, right? There it is, 2 pi FL. So as F goes up, X sub L goes up linearly. For capacitance, it's 1 over F. So that means we have a 1 over F type relationship between as frequency increases and as the value of reactance changes with frequency. So as frequency goes to a really high number, you'll find that X sub L also goes to a very high number, which is equivalent to saying X sub L goes to an open circuit. Similarly, as frequency goes to a very high number, X sub C, 1 over F, tends towards 0, which means as you go to that higher frequency, X sub C tends to act like a short circuit. Now, there's a lot more we could go over regarding complex number methods, power calculations, how RMS is determined, why is 2 pi F in the equation, and a lot more. But we'll have to wait for a later webinar. You can give us feedback, by the way, and say, hey, you know, I want to know some of this, or I would like to have some instruction on this. Just let us know if that's important to you. Okay, now let's jump. We got our 2 foundations laid. We've got Fourier, we have AC analysis. Now, complex versions for this AC system analysis. Can we actually use these complex numbers in all of the fundamental rules, such as Ohm's law and Kirchhoff's current law and Kirchhoff's voltage law? And indeed we can, and this was shown to be true, that not only is it a real-time evaluation, in other words, right at any particular moment, Ohm's law has to hold true, and so does Kirchhoff's voltage and current law, but also in terms of the phasor representation, they also hold true. So V is equal to I, not times R anymore, but times the complex number Z, or the impedance. And all of these are vectors. Similarly, Kirchhoff's voltage and current laws also apply with phasors. So the sum of the voltage phasors around a mesh or the current phasors injected into a node are 0. Now, since this modeling webinar is going to focus on AC network analysis methods and not real-time simulations like with EMTP or PSCAD, then we can remain in the realm of phasors, complex arithmetic, and nodal analysis methods. For efficiency, so that we can perform these calculations as quickly as possible, a lot of things were discovered. Obviously, making use of Kirchhoff's current law helps us to perform a nodal method. And what was determined was the most efficient ways for calculating were nodal methods. To do that, we have to build what's called an admittance matrix, or Y bus, that represents our network. We inject currents into a matrix, a vector, I, a current vector. Then we solve for node voltages in a vector called V, or the voltage vector. And we use the inverted form of Ohm's law to put these together. And that equation is that I, column vector, equals Y, the Y bus, times V as a voltage vector. And every element inside Y is just 1 over the impedance. And that's the relationship between admittance and impedance. Admittance is just 1 over the impedance. You might see that this would look like, for a typical 3-bus system, a column set of vectors, a matrix of admittances, and a voltage. We could write the first equation. There's 3 equations written here. I1 equals Y11 times V1 plus Y12 times V2 plus Y13 times V3. So there's 3 sets of simultaneous equations that we're representing here. For each current, admittance, and voltage, they are complex numbers with real and imaginary parts. The diagonal admittances are the sum of all the branches around and the shunt admittances at the node. And all the other admittances are transfer values for like Y12, Y13. These are connecting components between buses 1 and 2, and then here between buses 1 and 3. Harmonic analysis is going to make extensive use, and I probably said this earlier, but I'm going to say it again, it's worth repeating, of superposition. And the way we're going to perform AC and network analysis using harmonics is that each harmonic analyzed will need its own completely independent network model. Thus, for each harmonic that we just showed for this arrangement of using Y bus in a nodal method, the current vector at each harmonic is equal to Y at that harmonic times V at that harmonic. And so for each harmonic that we analyze, that's the reason why we need a current injection at each harmonic source location at this harmonic. So we have to have a full table of them and a network model at every harmonic H. So this matrix Y has to be built for every single individual harmonic that we want to simulate. And when we get done simulating, for instance, let's say we do 50 harmonics, one first to the 50th, there will be 50 versions of Y bus. And once we get done filling a column with all of the 50, making 50 versions of this and solving and generating 50 versions of this, then you can totalize your numbers because we're using the principle of superposition. The key advantage of a nodal method: speed of computation. You can do large network sizes. It's a convenient result form for calculating VTHD and ITHD, K factor, and everything. It follows the same form as the Fourier series. Again, with superposition at work, it works exceptionally well for quick ratings of equipment and harmonic duty, and it utilizes very well-known nodal admittance techniques, and thus is hardened for extensive and repetitive use. It's similar to the phasor methods. There's much more we could go over: how to build Y bus, how you can improve solution efficiencies, incorporate harmonic, Norton, and Thevenin. There are a lot of things we could go over, but we'll wait for a later presentation. Now, let's see what the time is. Wes, how am I doing? 10:43.
Fantastic, I'd say.
Okay, we're going to So, our foundation laid. Now we're going to jump into component behavior. Understanding how each of the components in the electrical power system behave is the absolute most pivotal thing when you're performing harmonic analysis and you're trying to interpret results. It's like any type of modeling that we do. That is, we want to build a model, we want to use it, we want to know the methods behind how that model was built, and we want to have an idea of what those results really represent and what their scope of application is. That's one of the most important things for engineers. I can use a short circuit routine that'll calculate all these fault currents, but boy, I can't use that for a power flow. Likewise, I've got a power flow and I can't use it to do a dynamic simulation. And so, unfortunately, today, we don't have a Star Trek holodeck, right? Where we can just say, well, put it there and tell me everything that's going on. We actually still have segregated tools. Each of our tools do one particular form of analysis, and we have to be very familiar with its scope of application. Along with knowing scope of application is what is it actually doing? Can I poke it, get a result out of it, and confirm that I know exactly what that is doing behind the scenes? And that is so important for harmonic analysis, because you're jumping from just a standard use of Ohm's law into applying Ohm's law across 50 different frequencies, okay? And so you kind of have to know how that is behaving and how each of those components are behaving at the different frequencies. So let's jump in. Again, key to harmonic modeling: knowing what components are needed, understanding behavior of each component, understanding that the majority of network components and their impedances we'll use are those typically associated with a short circuit study. Okay? It's kind of interesting. There's a lot of crossover between short circuit and harmonics in terms of the input data, and you'll see that. So for our modeling, we've got to at least review resistance, how it behaves, how inductive reactance, capacitive reactance, lumped inductive components. We're going to kind of group some things together. Same with capacitive components. We have to take a look at long line effects and how that's going to be affecting our results. We need to look at grid sources. In other words, the utility or whatever is feeding you electrical power. How does that look from a harmonic perspective? We also have to address non-harmonic loads and harmonic loads or harmonic sources. For all this work that we're looking at for the presentation, we're going to focus our attention on positive sequence, balanced three-phase circuit modeling. Now, if you ever have a need for unbalanced, that's kind of a little bit of a different beast where you have to pay a lot of attention to your data, not just in the positive sequence, but in the negative and the zero sequence as well, or possibly abandoning the concept of sequence and just looking at things from a phase representation, okay? Which they transfer back and forth, sequence networks and full impedance networks in three-phase. Those can transfer back and forth, but sometimes it's good to look at things from that phase perspective. So, resistance. Now, if you have a resistor bank and it's specifically designed to stay constant with frequency, then the model is R sub H at every harmonic is equal to some fixed value R. Very simple, right? So if it's made that way and there's no other effects going on and you know it's constant with frequency, then you just use this one value of R across all of the harmonic models that you'll build. However, there's two other factors that can cause a significant change to resistance and to cause it to increase with frequency, and that's skin effect and proximity effect. There's a lot, I'm going to just barely touch the top of this. There's a lot of details. I've seen some really good papers written on using finite element analysis that show how this works and affects the resistance and the equivalent value. But let's just touch on this, okay? So we have these two key effects, skin and proximity effect, and both can manifest in electrical distribution equipment and loads, and more importantly, in our harmonic simulation work. Skin effect is caused by eddy currents that flow unhindered within the conductor. So here we show a current in the conductor. We show it setting up a magnetic field around it within the conductor. And these eddy currents flow on the inside and produce additional heating. But on top of that, they tend to force the current to flow towards the outside of the conductor. Now, in reality, if you want to do this more complete, it's not drawn that way here, but it's a current produces a magnetic field, produces a current, produces a magnetic field, produces a current, produces a magnetic field, produces a current, produces a magnetic field. It's very continuous in this effect. And so this is rather simplistic, just showing one field line and one loop of eddy current. It's more of a distributed mush, okay? But the effect that it has is that it causes, again, the current to distribute itself unevenly within the conductor. And at a greater measure at higher frequencies towards the surface of the conductor. So at 60 hertz, we have most of the conductor flowing out in this area and not as much on the inside. And this is why ACSR, overhead lines, can have the conductor can have steel in the middle, right? Because there's not as much current here. So the losses aren't that high. You get up to 1,000 hertz, 400 kilohertz, you'll notice that the majority of the current is flowing towards the outside of the conductor. So this is why for an AM FM radio transmitter, the conductor that goes from the amplifier out to the antenna is a tube. There's no reason for it to be solid. It doesn't need to be solid copper or aluminum. You can use a tube to send it because there's not going to be any current flowing on the inside of that solid conductor anyway. So you might as well use a tubular form of conductor. The effective resistance thus increases because we have the same current flowing over a smaller cross-sectional area of the conductor, and that causes a net increase in both resistance and I squared R losses. Proximity effect, on the other hand, is caused by other nearby conductors, which impact this current distribution that we were talking about previously. Again, the same effect happens, and that is resistance increases with frequency, which also increases losses, and that's because the current tends to push outwards away from the center and to have where the proximity of the conductors closer to each other is causing this to happen. So in harmonic simulation tools, there's a lot of ways you can do this, okay? And there's two models that I'm familiar with that I've used extensively over the last number of years. And these are the exponent model and the eddy current model. Now, the exponent model is fairly generic. In other words, it allows you to select some base resistance and then some exponent value. And what it'll do is it'll increase the resistance at each harmonic according to whatever your relationship that you picked here. You could, the most common one, by the way, the exponent is 0.5, which for an ideal transmission line hanging in space, in Terman's Radio Engineer's Handbook, you can find out that it's square root of frequency. That resistance in the conductor increases by square root of frequency, so EXP would be 5. However, for transformers, and if you look at C57110 in the standard, you'll find this relationship where the resistance in the windings is increasing by the harmonic squared according to this relationship and this eddy current factor, this ECF number. So again, so this is more, this is specific to transformers, and this is more of a generic model. I personally like the generic model, and I've had great success with it in getting to match calculations. And I also like that it's slightly conservative. Now, if you look at these plotted, for 1 ohm of resistance, if we have an EXP of 0.5 and 0.7, that's this gray and yellow line. So excuse me, I'm in error there. It is the blue and the orange line. So EXP 0.5 is blue, 0.7. So you can see the resistance will go up faster, right, as you increase the exponent. And for the eddy current factor, you'll see that it has more of that squared effect that you see, you know. And that's because its exponent in that equation is by default squared, which is 2. But you'll see an interesting thing, and that is at the lower harmonics, the EXP method has a bit more effect. And at the higher harmonics, above the 15th, 17th, you'll see that the eddy current factor has a more significant impact on the resistance. Again, from my simulation experience, I've preferred the exponent model because it produces closer matches to the actual measured conditions. In other words, I'm actually benchmarking cases, an actual measurement versus a simulation. And when I've used the EXP method, I seem to get much closer. And as I noted, it is conservative. In other words, it's not increasing resistance as much, which means that the higher harmonics will have a bit more or a bit less damping, a bit more peakage to it. And you can see that here in this scan. Now, this is one of those points where I'm showing you something ahead of time. So I'm showing you a frequency scan. For those who know what it is, you know what this represents, but I address this later in the slides, but I have several slides where I show this. And sometimes there's some things in a presentation that you just can't get in a exact order. And this is one of them, because this really helps us visualize things. So just imagine that you're looking resistance changing over frequency in this plot. And what you're seeing is there's some type of a resonant condition in the network, and that's by these peaks, as you see here. And as you simulate with skin and proximity effect, as you go higher in frequency, you'll see that those resonant peaks are damped more significantly. And this is really important to simulate because this is what is really, truly happening. These resonant peaks never get this high, rarely, on a real system. That's because the resistance increases with frequency and gives us greater damping. Inductive reactance. So We looked at resistance and how it changes with frequency. Now let's look at inductive reactance. So we know earlier that X sub L is 2 pi FL. So it's definitely impacted by frequency. If we drop the J and just kind of look at that magnitude of that reactance, and if we were to review this at a couple different frequencies, for instance, at 60 hertz, we get 2 pi 60 L. However, at any harmonic H, that's 2 pi times 60 times the harmonic number, right? If this is 5 times 60 would be 300 hertz times L. Well, obviously, if you take the H and you factorize it out into the front here, you see that this is H times 2 pi 60 L, which is here. So in reality, this is as simple as it gets. The reactance of any harmonic goes up by H times the fundamental value of the reactance. That literally is it. And it has a very linear response. And when you run a harmonic analysis, if you perform a frequency scan, which again, we're going to discuss later on a network, and all you have is an upstream transformer, and it has minimal skin and proximity effect because the X over R is so high, you're going to see this, and you should see this linear ramp in impedance over frequency. And if you don't see this, then there's something wrong with the simulation. So this is a good benchmark to know about and to understand when you go looking at your tools and the results that you're getting out of them. Now, capacitive reactance has that inverse behavior. So again, if we ignore the J operator for now, and we just look at the magnitude of that reactance, then we see that we have 1 over 2 pi FC. And if we go through that same bit of algebra at 60 hertz in any harmonic, we find that the reactance at any frequency, H or harmonic H, is the fundamental value of the reactance divided by H. So basically, it increases as the harmonic number increases, the reactance drops by 1 over the harmonic number, and you can see that being plotted here. Oh, by the way, just to show that this was true, this is 1. By the time you get to 25, it's 25, right? It's linear. And by the time you get to 50, which is halfway through here, it's at 50. Similarly, here, 1 ohm, when we get to 5, it better be 0.2, and it is exactly. So 1 over 5 is 0.2, and that's matching exactly with what this representation is. So these are basically 2 of the fundamental relationships in all harmonic simulations. There just happens to be a lot of them. So if you build your network and you have a lot of these impedances in there, you'll find that they begin to interact with each other in interesting ways. But at the ground floor, if you do a harmonic simulation into a capacitor, you had better get this answer. And if you do a harmonic simulation into a transformer that has reactance, you'd better get this answer, okay? So now, let's kind of group this now into the component lumped inductive components. In other words, how many of our electrical power system components behave like this? That would be transformers. In terms of the reactive part, we've discussed 2. Inductive reactance, capacitive reactance. One is linearly increasing, one is 1 over the harmonic. The ones that linearly increase are transformers, reactors, motors, generators, and short conductors. And these components are modeled using both resistance and reactance with just a complex number. So for each of those components, you'll model them like this. The reactance at any harmonic H is H times X at 60, or 50, or whatever your frequency is on your system. And you can choose one of these type of models, and there may be even more models for modeling skin and proximity, or skin and proximity effect. But these are the 2 that I'm most commonly associated with, or that I've worked with in the past. I've looked at several really detailed papers on how to model this, basically knowing the the actual physical construction of the cable, the diameter, and all these things, and inner layers of conductors. But these work in kind of the general sense, and these are what we typically apply for harmonic systems analysis. The final total impedance is very simply Z equals R plus JX. And again, R is here, and these are some typical values that you can utilize for your work. I find that for overhead lines, 0.5, transformers, 0.7, motors, anywhere between here and here, cables, reactors, generators. So you can see everything is about in this 0.5 to 1-ish category, sometimes as low as 0.3. For lumped capacitive components, the electrical equipment will group in this category are just capacitors. Capacitor banks, capacitors and filter banks, or any form of capacitance without a specific model. And these components are modeled using, again, both resistance and reactance in a complex impedance model, but typically the resistance is very small and it is often ignored. So similar to the other one, or to the inductive components, the lumped inductive components, except the inverse now, X sub H equals X sub 60 over H, and the impedance is R minus J X of H. And R is one of these models that you choose. And again, we've shown typical values of the exponent. Now, no talk about harmonic simulations and the components would be complete without discussing long line effects. And I am not going to do a deep dive. This is going to be a very surface treatment, and it's going to provide, and I'll provide for you what the actual equations are that's used for it. But basically, long lines have to be simulated, in my opinion. You have to include long line effects, because short cables, short and medium length cables and overhead lines look longer at higher frequencies. So if you remember back in school, maybe you took a power systems class, and when they talked about long lines, I'm sorry, I forget where the break point was, but it was somewhere between 20 and 50 miles. You could do a short line model versus a long line model. In this case, my recommendation is for every simulation you ever perform, you use long line methods, okay? So for 60 hertz simulations, again, this is very little concern, but not for harmonics. However, one of the things to note is that it's not computationally excessive. So if you ever get a software program, and you'll find this to be true, that they're not modeling it, or it's not included by default, there's really no reason for that. Even from the very beginning, when we were performing analyses with matrices and doing it 20, 30 years ago, the long line corrections were really not excessive for a harmonic analysis. So why they're excluded, I'm not really certain. But again, I recommend they always be included for your harmonic analysis. And long line corrections are also called hyperbolic corrections, since they utilize the hyperbolic functions sinh and cosh. Now, as I just noted, unfortunately, many software simulators don't include this effect without special model additions or enabling the features. So care must be taken to make sure it is included in your harmonic simulations. Now, there's, again, a lengthy bit of theory to arrive at the adjustments needed to include the effects, and that'll have to be left for another day. But it comes down to these equations, and that is the corrected value of impedance is the uncorrected value times the hyperbolic sign of this value called gamma L. So length is important to understand, okay, in terms of the value that's gamma times some length L. And this is the value for the corrected value of Z sub C, which is this portion, RC and XC, and then YC, which is the admittance part, the shunt capacitance or the charging capacitance component, is this equation, 2 times the hyperbolic cosine gamma L minus 1 over ZC. When you build your model, it needs to be in a pi model form. RC, X sub C are in the series legs, and hung at both ends, a value over 2 is y sub c. Now, again, typically, the resistive part of this is equal to 0. So often this is only the reactive part divided by 2. And gamma L is defined to be this. And again, we're not going to do a deep dive into how that is true, but this is how it's done. Interesting, these are complex numbers. These are vectors. And since all the computations are in complex, here's a method to compute the complex forms of hyperbolic sine and cosine. And that's this expression here. So that's just been provided for your availability. CEXP is a complex exponential function that's in most, and I believe I need to qualify this, Fortran libraries, which is an old language. I think in C or C++, you might have to figure out how to construct this function as well. Okay, long line. The description, of course, is certainly not complete or fully descriptive, but the key is I'm indicating the need to properly simulate lines and cables, which make up a significant part of our electrical network. If not all, like for a distribution system, it's basically almost all of it, with the exception to some upstream transformers. The methods discussed that I provided are theoretically correct, and they've been validated through extensive use in a simulator tool, okay? And please note that these corrections are needed for each harmonic network that is being built. So for each version of Y-bus that I'm going to build for analyzing my system, I have to perform these calculations. I have to calculate this corrected value at each harmonic, all right? Okay, this is what it looks like with and without. So if you have, and this is an extreme simulation, I made this a really long line so I could show multiple resonant points. When you include long line effects, you will get a repeating resonance condition. It will peak out, it'll peak again, it'll peak repeatedly, and this will just continue and reduce in magnitude as it goes higher in frequency. If you only simulate the pi model without the hyperbolic corrections, you'll find that the first peak lines up fairly well, the first resonant peak of that overhead line or underground cable, but then past that point, it does not. Now, please don't get from this slide or pull from this Okay, can anyone hear me now?
Yeah, I got you, Dougie.
Okay, so finally I'm back. Okay, thank you. I logged out and logged back in again. Wes, can I hear you? Can you come on? Maybe he needs to do the same thing.
I saw him log off, but I didn't see him log back on.
Okay, hey everyone, we apologize. Can someone tell me about when I got cut off?
You were on your title slide. Title slide
on this
3. Yeah.
Well, that was convenient. That's good.
Yeah, someone's
Okay,
saying grid
you're
source
right.
up top.
There's no video yet. Let me share the screen here. You are correct. There we go. Perfect. Thank you. Thank you, everyone, for your responses. So that was actually very well timed for it to fail at that point. At this point, I would just wanted to have a moment for questions since we're at the top of the hour. Any questions? Nope, it's pretty quiet. Okay. We'll keep an eye on the chat and just let me know if you have any questions. Wes is gonna, and Alex will keep looking at it just in case to see if something pops up. And Alex, Wes, you guys just, you can just jump right in, and tell me audibly if you see something. Oh, I see the question about the PowerPoint. I'll leave that up to Wes. I think the slides first have to be reviewed internally before they're issued. But the hope is, yes, that we're going to be able to show the PowerPoint. You were talking about resonance. Can you go back to it? Yes, Francis. So we will be, you're going to see that, especially in the live example that we're going to go through. You're going to see resonance discussed a number of times. Absolutely. And how that occurs. Are L and C constant against frequency? Yes. And in fact, that is exactly the definition of the linear network. That is exactly what we're talking about. Those constants, L and C, being not changing as frequency is going up or down. Yes, that is exactly true. That's what we're trying to simulate. And that's what we are actually assuming for all AC network analysis, that they're constant. Interestingly, if for any of those you who still have any or have some familiarity with saturable core reactors, that's kind of a whole different beast that we have to consider if it happens to be available in a circuit that we're modeling. So if you are including something with saturable core, you may want to transition to a different form of analysis than an AC network analysis, especially if it's key and critical and important that change in inductance is simulated. Okay, so I'm going to jump into grid sources. Now, it may appear that everything so far is just very simplistic. And do you know what? That would be a good observation. The fact that reactive impedance XL just goes up linearly, and that the capacitive reactance just goes down by 1 over the harmonic number, it is a simplistic model. And that's important to know, because a lot of times we're thrown curves or results out of a harmonic study, and it's got these peaks and these valleys and all these results showing up, and you're like, wow, there's a lot of stuff moving around. True, but at the ground floor, this is how you model it. I can attest to that because I've modeled harmonic systems. I've written network analysis routines, and when you're simulating harmonic corrections, this is exactly how you do it. It's just that Y bus can get big, okay? I mean, it can get large. I mean, if it's 50 buses in your model or 100 buses, Y bus is a 50 by 50 array. Now, there's or 100 by 100. I mean, that's now we use sparse matrix methods and techniques to keep that from burdening us too much computationally. But yes, the network can get big, and these resonances can look a bit odd at times. Okay, so what we're going to transition now into is we've looked at a number of the components from their lowest level foundation. Now, the grid has kind of its own interesting factors to have to deal with. And in reality, the grid at a number of times, depending on how much simulation work you do and how much, you're modeling systems all the way up to the grid connection point, the source, the grid source can be also a source of contention. And that is it really having a significant harmonic impact or not? For a utility, okay, so let's say you're a utility and you're doing a grid analysis. Well, then absolutely, you'd better model a good portion of that grid, and it's essential for your analysis. However, for industrials with a main supply transformer, that's a significant amount of buffering impedance. And the question is that buffering impedance enough to minimize the effect of the grid where I don't have to really think about it? So this is compounded. This is compounded by the fact that a detailed grid harmonic model may not even be available to you or available in time for you to do your harmonic analysis. I run up against this all the time. Alex can attest to this. So these are some things we have to think about. Now, from the perspective that I have and having modeled systems for a while, I see 4 fundamental model types, okay? These are the most commonly that I think of in my mind. This is how I break them apart. Model 1 is a fundamental frequency short circuit impedance at the point of connection, the POC. And that's all. That's just it. It's extremely simplistic. Model 2 is a harmonic Thevenin equivalent. It uses a table of R and X at each harmonic at the point of connection. Model 3 are if you do a lot of utility work or if you're working with a large wind farm application in areas where utilities have supplied you what are called impedance polygons. These are defined on the RX plane at each harmonic at the point of connection. You're getting even a bit more complicated. And model 4 is you build it out in its entirety. Okay, or to the point where going any further doesn't matter. Okay, so you can look at these like this. These are how I look at the 4 models. The first one is nothing but R and X, and you model R according to skin and frequency effect, and you model X according to just the harmonic number times the X at 60 hertz. This is a very simplistic model, by the way, and is not truly representative of the grid, okay? But this is actually what I think probably 90% of people do, okay? Especially people doing harmonics for industrials, they'll often just ignore this. They'll ignore these details over here, and what they'll do is they simulate it very simply. Model 2 is almost identical to this, except each R and X is just in a table. And we have multiple scenarios we can pull from. And so we just look the value up. So we're at the 5th harmonic. We come down to here to the 5th. We pull out 94 and 143. We shove them in. So there's any resistance or change in resistance or reactance that occurs is just built into the table at each one of the harmonics. And as I said, you could have multiple scenarios for the different operating conditions of the grid. Model 3 is literally identical to Model 2, except it's just enormously more wide open in terms of what R and X might be. And so what they'll do is at each harmonic, they will supply you a polygon. And within that polygon, you can expect at the second harmonic, when you do your analysis at the second harmonic, you can expect it to be any number within this polygon. And for the third, it's a different shaped polygon, and it will have any number within this polygon. Now, how you select and where you pull from out of these polygons to do your analysis is a whole interesting conversation that we could have. Typically, these polygons are made by simulating thousands of cases in some automated script, okay? And they simulate all these, this line is literally hundreds, if not thousands of cases to build this characteristic. And then they say, well, we'll just put a box around it and say, you have to be within the box, okay? Again, pulling from these is very difficult. Model 4 is where you just model the whole grid. You model all the transformers, lines, cables, etc., as we have previously described, and you just build the whole thing. So, how do we choose the appropriate model, and what do we consider? Obviously, use the greatest detail that you have available, right? That just goes without saying. I mean, if we have it and it's available to you, use it, okay? Another point, consider that model 4, which is modeling the whole grid, is only practical for isolated grids. You know, if you were connecting to AEP or PG&E, I mean, where do you stop? You know, where should it stop? You know, where do you say that we've simulated far enough that we've captured what the resonant conditions of the network look like at our point of connection? That would be a whole study unto itself. And so if we kind of say model 4 is kind of out, you know, we can't really do model 4 because we're not going to model all 50 to 100,000 buses of the interconnected West Coast grid or East Coast grid. That kind of leaves us with models 1 through 3. So consider that you can't, this is really important, you can't really discern if the grid model will be significant without having the grid model, right? So definitively determining how significant the grid is mandates having that grid model. It's our catch-22 situation. I mean, you wanna, when you're doing a harmonic analysis, you're gonna say, well, should I do this detailed model of the grid, and should I expend the effort calling the utility and trying to get this information? Well, the only way you can know is if you have it, because you can't really make that determination. Now you might be able to do some sensitivity analysis, but just trust me, I mean, there really is no way to know. You actually have to have the detailed model to then say, oh, yeah, it doesn't matter. I could have done without it, but I'm sorry, that's just one of the difficult things that you're going to run into. It's one of the major catch-22s for the grid. And as I noticed, one of the points of contention that is happening here when we come to how do we model grid sources. So last point, given model 2 and 3 are kind of the area that we're going to have to stick in if we want any reality modeled of the grid, I would say never to fall back on model 1 only unless you've exhausted everything. And then in your analysis, in the report or the memo or whatever you write, just note how inadequate the model is, okay? Just say, hey, if there's anything going on with the grid, you know, we don't really know how this is going to impact us inside our facility or on this particular distribution feeder that has an upstream grid connection, obviously. You know, it's not the best model, okay? So model 2 or 3 is really where we should be spending most of our attention. So we should also consider that unless you're supplied all of the case results to produce those model 3 polygons, you're going to be unable to accurately determine coincident and realistic distortion levels. Where do you pull from in those polygons? Which X and R in each of those polygons at the 2nd through the 50th harmonic correspond to a realistic grid condition? There's no guarantee that any point that you could pull from that polygon, that point actually corresponds to something realistic from the 2nd, even just to the 3rd harmonic. So you have to be aware of that and understand how to apply those polygons so that you achieve some reasonable answers. I personally like model 2 the best, but you also have to consider how many of these tables do you need to adequately define the grid, because that's going to depend on the number of operating modes and what we consider to be normal operation and contingency operation. So you may require more than 2 or 3 tables to simulate, the different grid operating conditions and how that resonant characteristic of the grid will change. Finally, consider that the larger your industrial facility, if you're an industrial and you're listening, consider that the larger your facility is compared to the grid strength, the greater chance the grid's going to impact you within your own facility, okay? This is kind of hard to look at in terms of trying to extract the point I'm trying to make, but this is an actual realistic, this is some real data. And that's why I wanted to bring it up in this form. I'm going to focus on 2 places. One is this green curve right here. So I've got a system that I modeled, and it has a grid model. And at each one of the individual harmonics, 2, 3, 4, 5, 6, 7, etc. At each one of these points, I've got a data point for R and X. What I find is for this particular example, for me, that I'm illustrating here, is that for this grid model upstream, if I happen to have a 10 MVA transformer connected to it with an impedance of whatever I happen to have used, it may have been 7 or 8%, you'll find that this impedance curve with frequency is hardly changing, right? It is hardly moving. There's a couple bumps along the way. So in this condition, all of the variation of the grid is being masked by the buffering impedance of the main supply transformer. It's dominating the picture of the impedance. However, if we were to zoom in here between the 1st and the 21st harmonic and then zoom down low to 10 ohms, you'll see that for the cases of 50, 75, 100, and 200 MVA supply transformers, that down around the key harmonics, 3rd, the 5th, the 7th, you have a significant impact to that nice linear upstream curve of your supply transformer alone. And so you're seeing here that these large supply transformers are coupling you tighter to the grid because they have a lower impedance. And your buffering impedance is much smaller. And in this case, yes, including the model of the grid is completely essential because it's modifying the harmonic response inside your plant, okay? Now, we've looked at components all the way up to the grid sources, R and X, where X is inductive, capacitive. We've looked at how we've grouped them with transformers, grouped capacitors together. Now let's look at loads. This is like the last piece before we get to injections, which are the harmonic sources providing the harmonic currents. So for non-harmonic loads, you could go nuts trying to figure out exactly what you're supposed to do here. But what we typically do for our modeling is we consider them as constant MVA, constant current, constant impedance loads. Those are the most typical load models that are used in analysis programs. And then we also have 2 categories of induction motors and synchronous motors that I would like to address. So for these 3 load types, static loads, MVA current impedance, if that's how you've modeled them in your case, and you don't really know any details about them, okay, the modeling choice that most people make is to convert them into an impedance at the nominal voltage condition of the load. So you just, here's my power, here are my VARs, and this is the line voltage, the nominal line voltage, and then I calculate a value of impedance. And once you know what Z is, which is by our complex number, right? It's R plus JX. Now you need to choose how to logically process X for this load. Now, for all loads that are drawing reactive power, okay, which is probably almost all of them, except for the really odd thing that someone might choose to simulate where they put a negative, a leading power factor in the load. It's kind of odd, but it's there and it happens. You have to choose how to logically process X. Do you make it active inductive? Do you make it go up in frequency? Or if it happens to be negative, which tends to indicate there's some capacitance that might be in there, do you simulate a capacitant? Or do you just say, I don't care whether it's plus or minus, I'm going to treat it inductive at all times. So there's a decision that has to be made here on how you treat that load, all right? And of course, you need to include skin and proximity effect if you desire to. And that's modeled here with our two methods. So you choose one or the other, inductive or capacitive, and then choose the amount of resistance skin effect after you've calculated this net impedance Z for the load. Now, for example, a 1 megawatt, 1 megavar load connected at 13.8 kV, you can run through the equations from here, from this first equation on the page to here, and you'll generate that Z, the impedance is 95 ohms for each R and X. If you had a 0 megawatt load and a 0 megawatts and 1 megavar load connected at 13.8 kV, you're going to have 0 plus J, 190.44. So what I want you to notice here is that these are pretty high values of ohms, and that load impedances are typically very high in comparison to the effect of the short circuit strength of a motor locked rotor impedance. And so when it comes to load modeling, it typically has very little impact on a harmonic simulation, while noting that this additional real power that you put here will affect the damping of the network. So having loads modeled, especially the real part, will add damping, which is very realistic. Real power loads do add resistive damping for harmonic simulations. But again, their values of ohms are typically very high as in comparison. And I'm going to show that here in a couple slides. So now let's shift to induction motors. How would we model an induction motor? And the accepted practice is to take the locked rotor impedance with an X over R ratio, break it up into R and X at the locked rotor condition, and then for the X value, choose the harmonic number, just like we did for anything that's inductive, harmonic number times a locked rotor reactance. And the resistance, of course, using one of these types of skin and proximity effect simulations. I found that EXP for an induction motor is typically between 0.5 and 0.7. For a synchronous motor or a synchronous generator, it's very similar, except utilize the value X double prime D, which is the subtransient unsaturated D-axis reactance, X double prime D. And then the resistive part is the armature resistance, R sub A. And both of these you can pull from a motor or generator datasheet. Model X double prime D inductively and R sub A using skin and proximity effect. And again, the typical values between 0.5 to 0.7 for EXP. Now, as I was just discussing about how much more effect motors have than static loads. For example, let's look at this. 1,000 horsepower induction motor with a locked rotor impedance of 0.1667, which is 6 times locked rotor, connected at 13.8 kV, has this approximate reactance right here, 31.74 ohms. Compare this to the 1 megavar static load, which is 1 MVA. And if we fall back on the simplistic approximation, 1 horsepower per kVA, 1 to 1, which is a very, because the power factor and the efficiency get involved in, but you can assume for induction motors, just for example purposes, that there's 1 horsepower per kVA. So these are equivalent loads. You'll notice that a 1 megavar static load has 190 ohms. That is 6 times. So for the same amount of static load, in this case, for this locked rotor, which is 6 times, you'll find that the induction motor will have 6 times greater impact than the load. So that is why I would recommend that when you're modeling systems and you're going down towards the lower voltage on your low voltage buses at 480 volt, if you're having to model those, you should definitely include at least all of the motors in a lumped motor form. In other words, if you know that you generically have 385 horsepower of totalized across the line motors connected, use a model with at least 385 horsepower and a typical amount of locked rotor, such as 6 times. Okay, the last part of this is harmonic sources, okay? And this is where a lot of times you may end up having a challenge getting your data similar to the grid. When you get in the grid model, you're going to run into a natural challenge unless you're the utility and you happen to be able to produce this and produce those numbers for your connected customers. Harmonic sources, from my perspective, should in every case be supplied by the manufacturer. That's my recommendation that you do. That way, when you've completed your harmonic analysis, you can have a clean paper trail, and in your report or your memo, whatever you're going to write up, you can say, this analysis was performed, these are the results, and my data for the spectral current injections originated from ABC manufacturer, and here are those numbers, and document them in your analysis. It's just, this is an interesting thing to note. You can build your entire network 100% accurate. You can get every cable, every line. You get the long line model in there. You've got your capacitive stuff, capacitors everywhere. You've got everything. It's perfect. You know, and maybe even you've got some more detailed impedance data for the cables, you know, from the manufacturer, rather than just lookup tables inside a power system analysis tool that just you put in the length and the type of conductor, 500 kc mil, and then it comes up with RNX for you. Maybe you've got some real detailed data from the manufacturers on the exact amount of ohmage, you know, per 1,000 foot. And you put all this in, you build it absolutely perfect. If your sources of your injections are wrong, it's wrong. I'm sorry. This is like your single mode point of failure in a harmonic analysis. If your current injections are wrong, your results will be way wrong. If your network data is 10% in error, you're going to still do a pretty good job. But again, you could have a perfect network, and if your injections are wrong, forget it. You know, you're not going to get the answers that you really should be getting. So my recommendation, always get definitive numbers supplied by the manufacturer in terms of how much harmonic current is being produced by their particular piece of equipment. So let's consider 2 types of harmonic sources. There's a lot more, but again, I like to break it down into 2 solid forms that I see used over and over again. And that would be the straight current injection model and then the Norton source model. So for the current injection model, it's composed of nothing but pure current injection into the network, all right? Whereas the Norton source model is composed of 2 components. One is the current source, and the other one is the shunt admittance that goes with each individual harmonic. So for the current injection, its form would look like this, okay? And it's nothing but a pure injection, each harmonic injecting into the bus wherever it happens to be located. So if this is an adjustable speed drive, this would be your model. Let's say you have a StatCom or some type of a source inverter drive. In this case, you would want a Norton source model, and you have a current injection blended with an impedance that is hung on the bus. Often this is shown as an admittance, but when when you finally do the nodal analysis, you will invert Z into an admittance. But you could look at it from this form as being a shunt impedance. So for this, you need a table with all the harmonics. For this, you need a table, all the harmonic currents. For this one, you need 2 tables of all the harmonic currents that go along with each of the harmonic impedances and so you have probably magnitude angle. You're going to have 4 columns here, and here you're going to have 2 columns. Now, if you ever hear of using a Thevenin source model, that can be converted to a Norton source. And in fact, if a software program includes an independent Thevenin source model, it will indeed internally in the tool itself will be converted into a Norton equivalent source because it's going to perform nodal analysis. So what do we categorize as a current injection? That would be adjustable speed drives with diode or thyristor front ends, rectifiers, again, with diode or thyristor front ends, high voltage DC lines with rectifiers inverter using thyristor bridges, generic harmonic loads such as LED lights, fluorescent lights, power supplies, arcing loads such as AC arc furnaces, welders, and older style thyristor bar compensators. For the Norton source model, it's typically used for adjustable speed drives with source inverter front ends, wind turbines, again, with source inverter front ends, solar and battery inverters, which also, in most cases, are source inverters, StatComs and other fax devices that are using, again, source inverters, and anything declared as a Norton or a Thevenin equivalent harmonic source. So, for instance, a pure current injection model for an adjustable speed drive might look something like this. So you'd have data at a harmonic. You would have a percent of fundamental type value here. This is 3% of fundamental, 2%. And you would have an angle associated with it. In almost all cases that I perform harmonic simulations, I always assume my angle is 0 for every injection, and I will generate a worst case level of distortion, which is conservative. It is very rare that I will include angle. And that would typically only be done when I'm looking at multi-pulse rectification systems, and I want to simulate the cancellation of certain harmonics, like for a 36 or 48 pulse system. I have a plot over here of these numbers. And obviously we can tell, since the 5th and 7th are fairly low, that for this example set of data, it's predominantly a 12 pulse rectification system with some amount of residual harmonic distortion at the harmonics that are being canceled. Now, for a Norton source model, you're going to have 2 more columns. Not only do you have the amps with their angle, but in addition to that, you're going to have R and X that go along with the current at every single harmonic that you want to simulate. And if you notice between these two, I've been doing this with integers, 1, 2, etc. Arc furnaces, which is a really interesting load that you may have to simulate, and if you do, you have to make sure that you also include non-integer components. So these examples these are good for ASDs, rectification devices, switching equipment, and even some source inverters will produce harmonics at non-integer frequencies. And so you may find yourself creating a table with a lot more detail than jumping from 1 to 2 to 3 to 4. You may have to fill in the holes. Arc furnaces in particular are fully loaded all the way to the 11th or 13th harmonic in steps of 0.1. There's a lot of non-integer content in an arc furnace. And in our Norton source model, that may also be true. Here we're showing it in steps of individual harmonics, but for your equipment or for whatever's being applied, you may find that there are significant non-integer frequencies. I think I recently started or was performing parts of an analysis including cycloconverters. Cycloconverters, of course, have sidebands, if you're familiar with their harmonic content, and they vary as the load changes on the cycloconverter. They move further and further away from the center band at non-integer frequencies. And so you need to include that in your simulation as well if you have devices with cycloconverters and they have non-integer content. So this is not just an integer number. Here in this example it is, but you could have these being 1 to 1.2 to 1.3 to 1.4, everything as it's stepping through the harmonic spectrum. Okay, so any questions on that? We got about 15 more minutes. We're going to go through some harmonic analysis tools, and then we're going to get to the live example. I'll just let it, just open it up here for any quick questions. And hey, just by the way, everyone can still hear me. Just making sure. Someone let me know.
Well, I can certainly still hear you.
Oh, good, good.
It looks like there is a question that popped up in the Q&A only tab. I don't know if you're also looking there in the chat. There's one that popped up there.
We do not expect that the loads are connected directly. Do I think correct? I believe loads should be modeled at the right voltage levels with your step-up transformers. Yes, of course. Yes, if you're modeling lumped loads at a 480 volt, you obviously will have to calculate the correct impedance at that voltage level. Yes, exactly. Yes, you would have to calculate those impedances at the particular voltage of application. If you wanted, for instance, if you wanted to create a lumped model and you didn't want to have all the transformer impedances modeled discretely, you could find a way to add the impedance of the transformer into the load, right? You could just add them linearly together, and then you could create a net impedance at like a high side bus if you wanted to do that. Yeah, you'd have to do that probably on the side in a spreadsheet tool or something. Okay, I'll give it, do solar and wind generators generate significant THD to fundamental 60 frequency? It's dependent upon each vendor as to the amount of harmonic content they produce. They're typically on the lower end, but it can become significant. And that's one of the most important things to know about harmonics, and that is you could have a little bit of what appears to be nothing, but if it's in the wrong place where there is a resonant condition, it can amplify it into a problem. And I've seen this happen at wind farms where the wind turbines their source inverters are producing very little content, but there happens to be a underground cable charging resonance at the 13th harmonic or the 13.3 or whatever it is, and it happens to be sitting right on the spectral components from the source inverters, and it's growing it into kind of a nuisance problem. And there are ways that we can deal with that in terms of adding the correct type of filtering to tame and take care of that underground cable charging. Are we going to cover harmonic mitigation techniques? Nope, we will not today. In this seminar, if you read the brochure, it was specifically noted that we're not going to be looking at any mitigation methods, but if that's really desired from people, and let us know, we'll put another seminar together that's going to discuss mitigation philosophy and techniques and methods, of which there are many. There are many methods. Any other questions? Okay, nope. All right, so I'm going to jump into the last few slides that are going to talk about harmonic analysis and tools, and then we'll go into our live example. So let's go. All right, so there's many ways to perform harmonic analysis, but again, our focus is on nodal methods. But in general, you could use hand calculations, spreadsheets as nodal tools as one of the options, transient simulations, and transient network analyzers. Now that's a blast from the past. I'm not going to touch on that really much, except to say, if you know what a TNA is, then you're my age, okay? All right, hand calculations. Well, this just means you have some equations that are handy to you and you keep them available to yourself. For instance, here's how to calculate the resonant point, knowing the upstream transformer and a bank of capacitors in terms of their kVAR size. So here is an example, 6% 2500 kVA transformer with a 1600 kVAR capacitor bank. And it turns out it's resonant at the 5th harmonic. This is almost directly, 5.1 is almost directly on the 5th and would be problematic if you had 6 pulse ASDs applied in any significant number of sizes. How about spreadsheets? Spreadsheets supply more power and flexibility for computations, and even some frequency scans. And they're useful tools for things like harmonic filter design, adjusting your harmonic data, for getting it all prepped, presenting harmonic results, preparing case simulations, some educational stuff. There's a lot of uses for a spreadsheet, and I actually make pretty strong use of spreadsheets when I'm doing post-processing of my results. Consider this example where we desire to plot the driving point impedance, and we're going to talk about this in just a minute. This is like one of those scans that we've been looking at so far, and we want to say, at this point right here, at this bus, right where this ASD is connected, looking into the network, what does it look like? What does the network look like? And so this might take some explanation in a later webinar as to why this is true, but just understand that from a harmonic perspective and from a three-phase balanced perspective, this source impedance to the grid gets shorted to what's called the reference bus. And that is also true for this ungrounded Y capacitor bank. In the three-phase balance sense, it goes to what's called the reference bus. So these components are actually in parallel. The system impedance and the reactance of the capacitor are in parallel compared to the point of injection where the ASD is connected. So if we wanted to analyze this, let's first ignore resistance, because let's not work with the complex numbers quite yet. Let's just work with the reactive part. If we remember that reactance increases linearly, and 1 over H for X sub C for the capacitive part. So we note that X sub S and X sub C are in parallel, like I noted. The equation for the net impedance at the point of injection is the parallel impedance calculation. So if we're going to ignore R, it's 1 over X sub S, which is the system, minus, because if you remember, it's minus J, right? Minus J, and from the earlier definitions we talked about, 1 over X sub C. And what you'll find is if you were to put this in a spreadsheet, all you'd have to do is look at my harmonic number. I'm increasing by 1 to 1.1, 1.2, and I'm calculating X sub S. Look at 1. It's just linearly increasing, 1, 1.1, 1.2, and this value of X sub C is just going down by 1 over this number. So 1 over 31 divided by 2, right? 1 over 2 gives you 15.5. Now I calculate the net, and if you're looking at this column, this is this equation right here, just this equation, and this is the absolute value for the magnitude. And you can see this is what you will plot right here. You'll see a resonant point appear at the, 5.7-ish harmonic. And if you were to plot the impedance, this X sub S, and plot X sub C, here goes X sub C with that 1 over X characteristic, and here's that linear increase. And where they cross and where they meet and they're equal, that is where your resonant point is. And that's your natural resonant equation. This is a tank circuit. And what happens is when these two values are equal, since they subtract from each other under the, and because they're in the denominator, this will go to 0. 1 over 0 is an extremely high number. It's infinity. Well, it doesn't quite, in reality, there's some resistance in here. So it never goes to 1 over 0. But if these are ever exactly equal, you'll have a 0 divided. And fortunately, in my stepping, the way I did stepping, I never hit that exact point where they were equal. But you can do that numerically. You can get to just the right values and make this go undefined here, this resonant point. So one thing to note about this simple calculation in the spreadsheet is because I left out resistance, I don't have any damping. So it creates an excessively high, unrealistic peak. So this simulation would not be good for calculating what the actual distortion values might be. But it is good for seeing where the resonant point is and what its characteristic looks like. Okay? So what about nodal Y-bus tools? So as I've noted, these are extensively used for harmonic simulations. They supply excellent method to blend large network sizes with reasonably accurate results, ability to produce both network impedance scans we're going to talk about and various distortion results. They have great speed, and they rely upon time-proven methods. Let's skip some of these slides because I've kind of already covered them, and I've talked about, remember this earlier, where I showed Y-bus and how you use the modified form of Ohm's law right here to be able to calculate with the voltage vectors. You'll use a process called Gauss elimination to get them. And each harmonic has to be analyzed, as I noted earlier. Here's an example. Here's nodal Y-bus being applied to a wind farm in a software called Easy Power, if any of you are familiar with it. And I've built the entire model of the wind farm. And so if I zoom in on this piece, you can see it here. It's pretty detailed. It models all the components that I want to have. And I did what's called a frequency scan on the main bus. And I discovered that there's a resonant point, and that if I added a C high pass filter to it, I can damp out that resonant point, okay? So what about transient simulator tools? Now, if you ever plan on using these, you're going to be getting microsecond level simulation results. And the key advantages are you get all this detail that you may not have had in the typical nodal analysis that we use for AC systems. All the phasing is included for transformers and loads and harmonics. All of that is automatically included. But you can only have a limited network size because it's simulating at such a fine level. You can't put 1,000 buses in here, or even 100. I mean, it's going to take hours just to get your simulation done. But it does let you simulate all the switching action of thyristors and diodes and IGBTs with exceptional detail. And it needs post-processing. For example, here's a 12-pulse rectifier, and I can get a great 12-pulse spectral content out of it. I mean, a waveform. No spectrum, just the waveform. Now, to get the harmonics out of this, I have to perform some type of Fourier analysis to be able to get it. So now I have to post-process it. I have another example here. This is a 36-pulse arrangement with 3 12-pulse rectification systems with phase-shifted transformers. Upstream of this, I have to see what the total current is, and if I want to judge it, I have to analyze it. And they have those tools, for instance, in PSCAD. That's what I've been showing you. It has an FFT, a fast Fourier transform to take the waveform, just like you would do with a power quality meter. Literally, just like you would do in the field. You'd hook up a power quality meter, measure the current, and shove it through an FFT, and then generate the spectral content. Maybe if you do a little bit of extra work on your own, which I've done here, I can show the IEEE 519 compliance limit in red, and then the actual harmonic content of the current being delivered out of that 36-pulse system, and I see that I have a number of violations in this case. Okay, now, actual simulation methods. What are the key methods we are going to use? Now we've got this background for modeling. We kind of understand, we've got this foundation set for each of the components, how they're going to behave. What are those key tools that are typically used for harmonic analysis? They are frequency scans, harmonic current flows, distortion bar charts, and distortion calculations that turn into metrics like total harmonic distortion of voltage and current, summation, RMS, transformer deratings, K factors, etc. Frequency scan is where we go to a bus. We pick a node somewhere in the location that is important to us, like the main bus of our plant, or like the main bus back at a substation, or maybe a load center and it's fed from 480 volt. We want to look at the load center. We take a look at that bus and we perform what's called a frequency scan, and it tells us what the network and the network only looks like. There are no current injections being modeled except for one, and that is where you're going to perturb it. So you're basically building a network, you're going to go to a location, and you're going to say, I'm going to cram in, I'm going to push into the network a source, typically 1 per unit, as I note here. And then you're going to step frequency little by little, starting, for instance, at the fundamental or first harmonic, then you're going to go to 1.1. You're going to rebuild the entire network and inject that same amount of current. And you're going to continue this. So you're talking hundreds of individual network simulations just to show one frequency scan. At the point of injection, we can then take the resulting voltages from the simulations and divide them by the current that we injected, and we get the impedance at that point. Now, interestingly, if you inject 1 per unit at angle 0, this is V over 1, which means Z equals V. So in the per unit system, when you're done with the simulation and you have your resulting vector or your voltage, it is Z, because the injected current by choice was made to be 1. The result's called the driving point impedance and represents the impedance of the network versus frequency at that point of injection. When plotted, it helps us quickly determine where resonant peaks or filter minimums are at that point of injection. Again, there's no other injections being modeled from any harmonic sources. This is purely a network impedance condition. If resonant peak coincides with a harmonic source injection, then one can expect harmonics in that area to be amplified. Likewise, this is really, really key. If there are no harmonic source injections, then resonant points are never excited and no distortion will be present or amplified. If you have a system, you have no harmonic sources, there's almost not a need to do a harmonic simulation. Harmonic work is typically for those systems that we know have some form of harmonic source involved. So here's an example of a group of scans where I'm trying to determine what value of resistance I'm going to put on a C high pass filter. It's got a 5th and a 7th and a 36 C high pass. And in this case, I was varying resistance between 20 to 70 ohms and trying to figure out, what's the most optimal value for me to use in my filter. Current flows are similar. We're going to the next simulation technique, which is called a harmonic current flow. And in this method, what we're going to do is treat it almost like a power flow, except we're going to show currents instead of P and Q. So we're going to pick a frequency. Now, you could choose fundamental again if you want to, but there's no reason to because we have a power flow answer. So typically we would choose a harmonic, something like the 5th or the 7th or some harmonic where we think there's a problem. And then we'd look in detail as to what exact currents are flowing at that harmonic condition. So this allows us to see current flow details that are going in equipment, exiting to the grid, drawn in by a filter, etc. This type of detail is really key to understanding resonant amplification and filtering and series reactance calculation. If you, with your harmonic tool of choice, whatever it might be, I must hope that it would have a harmonic current flow. Use it. Use it to get a good feeling for how your network is responding and what's really going on when it comes to points of resonance. For instance, in this example, consider this really simple system. Upstream transformer, motor, capacitor bank. If I do a frequency scan and I inject current at this point, ignoring any other injections from anywhere, which in this case, there are none, right? There's no harmonic sources. I have a 20 MVA transformer, 9% impedance, and I have a 7.5 megabar capacitor bank. And of course, I did this on purpose. I sized this bank and this transformer impedance so that I would resonate at the 5th harmonic. I did that on purpose because I want to show you what happens at the 5th harmonic as far as the currents. In this harmonic current flow, notice all I'm injecting is 1 per unit. But again, the resonant point is at the 5th harmonic. So I want to do a current flow at just the 5th harmonic. And at the 5th harmonic, 1 per unit current ends up producing 20 times the amount of current flowing through the transformer. And 22 to 23 times the current flowing into the capacitor bank, and a small amount involved with the motor. So if you were to add all of these currents up at this node, they will equal 0. Norton's current law will be met at this bus. And so what this is showing you is why resonance is such a big deal. If you happen to hit it in the wrong place, which does happen a lot in systems these days, you can end up with 20 times, 10, 20, 30 times the amount of current flowing in pieces of equipment. If you take careful notice, and you have to pay attention to these arrows and what direction they're going, you'll discover that this current and this current are 180 degrees out of phase. So at a resonant condition, when you're hitting this really high resonant amplification, you will find that these currents are almost exactly equal and 180 degrees out of phase. And that is exactly the condition that happens during resonance in resonant tank circuits. And again, 20 times. So it's not a little bit. So, if you had any significant amount of fifth harmonic, that fifth harmonic is going to be amplified 20 times. Distortion bar charts. So these allow us to visualize distortion harmonic by harmonic instead of through a totalized figure like voltage THD. And these plots are what help us determine what frequencies distortion levels are being caused by. In other words, if you say, oh, I've got 8 or 9% voltage THD, yeah, well, which harmonics are causing that? If you just get the THD figure, you can't see it. But if you get a bar chart showing you which individual harmonics are producing it, that's a bit more helpful. And normally we review these in percent of fundamental. Now, for voltages, for currents, I recommend using amps and not percent of fundamental, just because if you ever want to do any post-processing, you can put these amps on any basis that you want. And that's particularly important when you're coming to like IEEE 519 compliance, and you have a base that has to be applied according to the standard. Then putting them out in amps is more useful. So for instance, this is that a similar example, but instead of a motor, I have a 2,500 horsepower ASD down here. And it happens to be 12 pulse. And this resonance looks like it's just because of this capacitor bank is just above the 11th, right in the problem area, which is where the 12 pulse drive will produce 11th and 13th. And as seen in the THD on the bus, you can see that during this simulation that I'm getting over 8.5% voltage THD. But which harmonics are they that are producing this voltage THD? If you do a bar chart plot on the bus voltage, you'll see that the predominant component is 11th and that the 13th is a little bit smaller. Okay? Look at the THD, 8.577. This one is just above 8. Magnitude rules in THD. THD is the square root of the sum of the squares of all the harmonic components, and that squared nature of it basically makes the largest value rule the distortion. If these were equal in magnitude, they will share how much of the distortion, a lot more. But in this case, you can see that even though you have 3% THD down here, and this is 8%, the 3% is only adding 0.5% to the THD value. So THD, similar to RMS, has the ability to hide answers. You kind of see what I mean? Yeah, it's 8.57, and the 11th is nearly 8, but it's hiding the fact that there's significant significant 13th harmonic here as well. So THD has to be looked at carefully, and getting a bar chart like this really helps you break it down. Now, distortion calculations, I think we all have some, familiarity with. We hear them used all the time. And I just showed you here on the previous one line, I showed you a distortion value in the Easy Power software being put out on the bus. It really depends on the tool of your choice, how they're going to be presented, whether they're on the one line or whether they're going to be in tables, and whether they include them for THD and current, or which numbers they're going to put out and to present to you. So the tool that you utilize may be similar, or maybe there's alternate methods like report boxes. I don't know if you've seen tools that have output result boxes, and you select the node that you want to look at, and it presents all the results in a table in a box. So there's a lot that we could say about, we could go into definitions of every single one of these distortion indices. But again, we're going to have to save that for another webinar. But the key values, a number of the key values that we utilize are voltage distortion, current distortion, what we call a peak voltage stress measure, which I call V sum, the root sum square, which is equal to the RMS, except it's formed from harmonic numbers, not from the waveform itself. And we call that root sum square voltage. A root sum square current IT product, which is a telephone interference, which is mostly for the old days when they had telephone communication circuits, but you still see this pop up every now and then as a method by which you can maybe reduce interference if you want to. Transformer deratings, C57-110, transformer K factor from UL 1561, conductor derating based on harmonic heating, losses, which include fundamental and all harmonic losses, IEEE 519 compliance checks, and there's a bunch more that you could probably come up with, but these are a number of the key ones. So just a couple minutes here for any questions at this point before I jump into a live analysis example. I'm actually going to pull up a software tool. We're going to prepare our data. We're going to do all these things and show you how I would actually proceed through an analysis. Any questions? Do multiple subcycles switching tuned harmonic capacitor banks cause a harmonic concern? Subcycle switching. Okay, so that's a transient condition. Okay, so if you're concerned about the switching of a filter or a capacitor bank and whether it's going to cause a concern, you need to perform a transient analysis to see how the voltage on the waveform might peak or how fast it'll ring and how long that will last. That's not a harmonic concern. Harmonic is like a steady state condition that we want to simulate and understand. Yes, it does vary slowly over time in most cases. Well, for arc furnaces, it varies quickly a lot, but we still analyze it from the AC perspective as something that is fairly long lasting, and it's not a subcycle transient condition. This covers steady state harmonic contributions. How are transient harmonics analyzed and addressed? Again, for energizations, you would have to use a transient analysis program like EMTP or PSCAD or something similar, or even maybe put together your own transient simulation in Excel, which it's fun to do. It's a possibility. You get a lot of rows out of it to simulate that short, that much detail. But yes, you'd have to use a transient simulation tool for that. Any others? Okay, since no other questions, I am going to jump into the live example. Oh, let's look at just a couple slides to prep us for it. So in this live analysis example, we're going to be using the Easy Power software and spreadsheets for the pre and post processing. Now, Easy Power for NEPC has been utilized extensively for years for studies and filter designs. It is not the only well-designed tool for harmonics, okay? But it's fast. It's fast system building capability. In other words, how fast I can build a one line and get data in helps us to model and simulate the mini systems that we need to analyze. So we're in the condition where we could be analyzing 50, 100 systems a year. So we need a tool that really helps us build them fast and quick to get results out of. if you're modeling your one system, but you need a lot more detail about it, you can also use other tools that possibly have Python scripting. For instance, Power Factory includes Python scripting, which is a feature that EasyPower lacks, which is valuable for performing analysis across a large number of cases and through which analysis automation can be programmed. So you're going to pick a tool that's going to be working best for you. And when you do, again, I've got one more slide past this next slide here that I want to show you, that I want to make a comment about that in terms of the tool that you pick. So in this live example, we're going to get our data sorted and ready. We're going to build, well, most of the model. I don't think you want to watch me build the whole thing. You know, that'd be a bit boring, but we'll build enough of it to get the idea. Then we're going to review some harmonic measurements. And from those measurements, we're going to develop some current injections, and we're going to benchmark our model and make sure it's performing well. Then we're going to look at some impedance scans that I've talked about and see how they inform us about what's going on with our data and our system. We'll perform some distortion calculations, some THD, and then we'll also at the end produce a chart that shows IEEE 519 compliance checks. So the model is going to look like this. This is the main part we're going to analyze, which is in blue. And over here on the left side, I've mimicked or tried to fabricate a reasonable approximation of what a grid might look like. So we can see when is it, you know, when does it matter, when doesn't it matter on this example. So we'll take a look at this as well too. I'm not gonna build all this. I've already built it, and but we'll just include it in our model so we can take a look at that, the whole grid perspective. So one final disclosure and a recommendation. So some of you may know, I don't know if you do or not, but I said in my information earlier on the brochure that went out that I was previously employed at EasyPower. So because of that, I have a bit more trust in it, in its ability to simulate systems correctly. My work at EasyPower included specifying and testing the actual Harmonic tool, and then for 15 years maintaining it and improving all of the engines within the EasyPower package, including I actually added the dynamic stability feature in that tool. I added the DC simulation part, and so I'm very comfortable with it and know kind of its quirks, its ups and its downs in terms of what type of results I can expect out of it. And on top of that, I have simulated hundreds, if not thousands, of systems using it, many of them where I took actual field measurements that I took myself and then came back and did system modeling and benchmarking. And I've been able to match those results from measurements versus a model a number of times, and so I have a lot of confidence in it. So most of you, I presume, may not have that same similar experience to draw from. So I highly, highly recommend that if you have not already, that you vet your own software tool of choice before performing any significant analysis. I really recommend this. Benchmark it. Benchmark it against other harmonic analysis tools, benchmark it against hand calculations, spreadsheet calcs. What you expect to see out of that tool, do it. This will help you build familiarity with it, understand its odd behavior, and apply it with greater understanding. Just so you know, as an example, after coming to AMSC, I was starting to build systems with the Power Factory software. I literally benchmarked an entire wind farm in Power Factory against EasyPower because I had greater familiarity with it. And I wanted to see for myself how they would compare. And I basically got one-to-one, both of them laying right on top of each other. Just slight differences because of the resistance skin effect and proximity effect was modeled slightly differently there. And but as far as the resonant points where they occurred and the general amounts of amplification, it came out to be almost exactly the same. So I benchmark it. I have a good feeling for how to model inside that tool now, and feel more confident in the answers that I'm going to get out of it. Okay, let's pause the presentation. And what we're going to do is we're going to jump to the Easy Power software. Now, I've already built this network for us, but what I'm going to do is show you how I would actually go about this and build part of it for you. And then we'll come back to this finished build and do the majority of our analysis. So I can zoom in here and, of course, see the different components that I've modeled. And in addition, what I've done is I have created for myself a spreadsheet where I'm going to set up all the data that I want for my study. So we've got a study. We've been asked, analyze this system. So you need to get data. You need to get transformer impedances. You need to get lines and cables, their lengths, the type of conductors that are there. You need the utility grid model, if they have one. You need the spectral content for your injections. So let's take a look at that. Let's see how we might get each of those pieces of data and how we would incorporate it into the software. So I have a number of tabs here. And just so you know, in terms of the utility grid equivalent that I came up with, I made it myself. And I'm showing here how an actual scan, if you see this scan here, the orange line, versus the individual integer numbers that I pulled out of the scan are laying right underneath it. So I just proved to myself that, you know, my table is going to work well. And the table of data is right here. It goes all the way down to the 50th harmonic for my grid equivalent. So I'm going to say new and create a new one. And so I personally like to start from top down. That's kind of my, I think that perspective when I go out in the field and I perform analysis, I take measurements, or I review a network, I always like to start top down. So we're going to do that in the Easy Power software and start with a utility source. And then we're going to add a bus, and it's going to ask me what KV, and I'm going to say 230 KV. Now that I have this information, I have modeled on the left-hand side 3 different sources. One is the simplistic one. Remember we talked about the simple source with just a short circuit impedance? Okay, I'm going to come into here. I'm going to say that it is 3410 MVA, and it has a 15 X over R ratio. Now, I perform harmonics in positive sequence. Okay, that should actually be, that's a typo on the left-hand side. It should be 3410, and it should be 15. I'm not simulating the difference here, and in the harmonics analysis program that I'm not going to do any zero sequence work. I'm going to do everything in the positive sequence, so it doesn't matter what the zero sequence value is. It's not even going to use it. So on this source, I'm also going to add 2 more. And for these, I have to include the grid equivalent model, right? I'm going to put a switch here so I can make them open under normal conditions. And I'm going to open and open. Okay, I've got my source model, but I still need the grid equivalent model. Since I have the data, it's been made available to me, I definitely want it. So I'm going to come here to my spreadsheet, and I'm going to say I want, for scenario 1, I want these. And I've done this on purpose in this order. So I can just come to Easy Power, double click, go to the harmonic source, and call it table values in ohms, and hit Control D. And I just put it in. Boom, right there. I'm done. This one, by the way, is 3410 MVA. Do you know what I'm going to do? I'm going to do that over again. I'm going to say copy and paste. I'm going to overwrite those values, and I'm just going to put them in again. Harmonics here, table values, ohms. Boom. Okay, that way I copied over the MVA without having to type it all in again. And I will copy, and I will paste, And then here, I'm going to make this 593. And this will be, these short circuit NVAs will be overridden, and they will not be utilized in the harmonics calculation if you include the table. That's just how this particular software package works. I will come over here, take these values, Control C, come over, go to this source, harmonics, table, ohms, inject, boom. I have now added my grid model, okay? And I've got two scenarios. I've got this simple model that doesn't have the table, then I have these two that do. Now I'm going to add my transformer. And now I have to know what this data is. So I would have received it from the either the nameplate. I'll go out in the field. I'll grab the nameplate on the transformer, and I believe this is 34.5 kV. And I would grab that information off the nameplate. Now they typically don't have the X over R ratio on the nameplate, so you'd have to get the transformer data sheet to get that information. So this is a 30 MVA transformer, and the impedance is 8.5%. And I'm going to hit this calculate button, and it'll automatically determine a generic zero sequence number and a generic X over R ratio from the red book. And I hit OK. As you can tell, I probably have too much familiarity with this software, right? Okay, so what I'm going to do now is I've got some long overhead lines. I have 1.5 miles, and I have 2 miles here. And I'm going to model one of these, and the rest of them, I'm going to just jump back and use this model, but I'll show you how I would actually build this, starting with at least one of the lines. So I would put it in overhead line. Once I've got my overhead line in, put a bus at the end. And I would choose it as 397 LARC, ACSR, size 397 LARC. Hit the calculate button, and it will populate the impedances here in ohms per mile and mega ohm mile for the charging component. And I'm going to say this is 1.5 miles. It automatically generates your ampacity as well. So you can tell this is set up for more than harmonics. I mean, this is going to help you perform power flow simulation short circuit. Interestingly, on this bus, there is also a capacitor bank, 1200 kVAR. kVAR, 1200, enter. Okay, I'm going to put a switch on here in case I want to turn it on or off. Now, I'm not going to continue like with every single one of these subsystems, but let's take a look at, actually, I want to do this main one. No, I'm going to do the small one. That way we can get into analysis and maybe some additional questions on the analysis. Okay, so let's model this system. Again, put a transformer in. Did that not insert transformer? Here we go. And secondary voltage is 480. As I may have noted earlier, for low voltage systems, I do not model the, most of my analysis is involving medium voltage networks. And so the detail of the low voltage is not as critical, but I know what parts are critical. Motors, connected motor KVA, static loads as a lumped value, both of these as lumped numbers. Motor of across the line motors accumulated, across the line ASD accumulated into one, and then all your static load that's remaining accumulated into a separate value. This gives you some detail down here without having to simulate the whole 480 volt network. If you're doing an analysis on the 480 volt network, you should simulate it in greater detail. Okay, you understand? I'm not, this is just extra information. And by the time this load and this motor go up through this transformer, the transformer has a significant amount of impedance. These are going to be seen as less important. But the current injections from the adjustable speed drive, the harmonics, are definitely going to flow up and accumulate onto this bus. So I want to include those. So this is a 2500 kVA transformer, and its impedance is 8%. You can see what I'm doing to put the numbers in. And then let's put in 2 motors, 1, 2, and a static load. Here we go. A little bit of neatness here. And for this one, it is a 500 horsepower. I'm going to use all the generic numbers in here, not really worried about too much of it in detail. The power factor of an ASD, however, is typically rather high, like 0.98, and I didn't even include that over here. I probably should have. But so you may want to adjust the power factor so that under power flow conditions, which are used at fundamental conditions for the harmonic analysis tool in Easy Power, you may want to have that modeled correctly. Short circuit, I just do a generic number here because I'm not going to be using any of that data. And then if I go to the harmonics, I find, oh, I need some spectral content. Well, in my setting up of this case, I got some information from the manufacturer. And that data is, actually, here's my plant loads for plants A, B, C, and D, the horsepower. I've broken them up by ASD, motor, static loads. And for the 4160, just the ASD and the motor. And you can see how I've broken up this data so I can enter it into the program. But then I need spectral data, but I haven't taken my measurements and processed them yet. So let's just leave this blank for now. We'll leave a holding place for it. Oh, but the one thing I didn't do was call it adjustable frequency drive. So that's what you do in Easy Power. I don't know how you spec sources in the many other different software packages. A Power Factory, you have to give it as a particular harmonic source. But in Easy Power, you can build it in with the motor. And so that's what I'll do here. These are cross-align motors. I'll say that they're 700 horsepower. And I'm going to use the default locked rotor value of 16.7%, which is 6 times locked rotor. If you know that the average locked rotor here is only 5 across all of these, then put in 5. Okay, and the static load is 700 kVA. Let's kind of see what it's broken up into. It is a power factor of 0.9. So I will put in kVA and power factor, 700, and the power factor is 0.9. Oh, you see that I've built this part of the system. I'm missing my spectral content. I got a capacitor bank in. Important. You must model every capacitor bank on a system. Just don't try to skimp. You'd be surprised where these will manifest and cause problems. Another interesting point. If you have no capacitor banks and you have no really super long cables that cause significant cable charging, you will have no resonant conditions. If you have no resonant conditions, then the distortion calculation you see up here will be due only to the upstream transformer impedance. And if you need filtering, it's just because the distortion is too high under normal, just non-resonant conditions. For every capacitor that is on a system separated by an amount of inductance, like a line, like here, these two capacitor banks are separated by this 2-mile line, you will get a separate resonant point for each one and with the separation of reactance. And you're going to see that when we perform frequency scans on this. So I went out in the field and I took some measurements. Obviously not real measurements, but let's pretend I went out in the field and on this transformer secondary, which by the size of it, you can tell that this system looks like it's a distribution network, right? Yeah, 30 MVA transformer at the substation, 8.5 impedance, 8.5% impedance. So let's say I took some measurements here. It would be best to take measurements at each harmonic source, each one. That would be a better approach because then you know what each one really is and you have the detail of the breakdown. But often, you know, we got to work with what we have. And so let's look at the case where I've measured harmonic currents up here. I know that all the drives here, here, and here here, over here, are 6 pulse. And I know for certain that this is a 12 pulse drive. I just happen to know my clients in the network. I know what their harmonic sources are, and I know that's what I have. If I have measurements up here, I could do a first type approach at guessing what the spectral content is down there based on what I have up here. And I've done that here in this spreadsheet. These are my measured harmonic currents up at the 34.5 kV level. And so what I did was I said, well, each of these are 500 and this one's 2,500. Let's just divide the harmonic content up by how big each one of these are. So that's this first set of data. So you can see that the fundamental is broken up here between these three, and then this one is 130 because it's 2,500 and not 5, right? Similarly, the fifth harmonic current, 6.5, is broken up evenly between these three, and then more for here because it's larger. But this is a 12 pulse drive, not 6. So the 12 pulse content, or the 12 pulse drive itself, would cancel, significantly cancel 5th, 7th, 17th, 19th, 29, 31, 41, 43. And so I have to say, well, how do I take that into consideration? This is how I did it. I said at the 5th, the 7th, 17th, and 19th, that in reality, it's like having 3 500s and then this one just being a really small drive because it only has residual 5th and 7th. And that's what I did here. So you see here, in these rows, I have replaced 5, 7, 17, 19 with a different breakdown where the majority of the 5th goes to these three and just a small amount of residual goes over to the 2,500 horsepower. So these are my final amperes. And then if I take each of them and divide them by the fundamental current basis, I end up with a table that says these drives have this amount of harmonic content and this ASD has this one. So I have a table of content, now spectral content determined from an actual measurement, and I just have this fake column full angle full of 0 just in, so I can copy and paste into Easy Power. So I'm going to take this number, this column. Excuse me, I have to come over here and I need harmonic numbers. So the best way to do this, to make it really quick, is I would say equals this. I would put the spectral content here because it's going to be 3 columns in Easy Power, and I'll say this equals here. And then here I would say equals the angle 0. And now I have 3 columns all set with the information that I want. Right? And I come here and I say copy. Control C. I go to Easy Power. I go to the drive. And I go to Harmonics. And I say, this is all fine, set up the way it is. And I say Control V. And now I have populated the content inside Easy Power from the 2nd up to the 50th harmonic. Okay, and you'll notice that is exactly what I did over here. Same values. You see them? There's that 31% of the 5th showing up. So that's the same values. Okay, so I've added spectral content. I've broken down my 40 volt load. I've modeled part of the system, right? Transformer. I put in an overhead line. I put in a capacitor bank. Everything else here is a repeat of that. And in fact, you'll notice in my example, it's kind of repetitive. These are all the same, right? 5, 7, 7, 5, 7, 7. I made these identical so I could just copy and paste. And the only difference is that I would have a different spectral content for this drive, and this drive is here, Harmonics. And here you see 2nd through the 50th, and I believe the 11th is the highest harmonics at the 9.0433. And if you look in my table, That is this value right here. So I just copied this column and put it inside here for this harmonic content. So I have injections, I have a network. At the main bus up here, I also am simulating a capacitor bank at the substation. 2400, 2400, 2400 kVAR, 3-stage. Okay, I'm not going to model that in here because you could see that would be easy to do, right? Add a cable, add a bus, add each of these, add a switch to each one, and just put each one in at 2400 kVAR. So let's not go there and build that, but now let's transition to using this model that I have built for us for the live analysis. Okay, let's start our work. We built our model. What's going on? The first thing that I would do is in Easy Power is I would perform a frequency scan. I would come over here, I would put my system here, and I would say the most important bus for me is the main substation bus, and I would double click on it. Now notice something. At the substation, one stage is on, and out on the feeders, cap bank is on here, cap bank is on here. That is what my scan looks like. So my frequency scan is telling me at the main substation bus for this condition of the network, my resonant point is somewhere at the 8.2 harmonic. See, I'm looking at this thing up here. 8.2 harmonic here, and then I have another one out here around the 28th. Not as bad. And look at, it's got a kind of a damped out peak because of the modeling of the resistance in the network and the resistance skin effect and proximity effect. So what would happen, and this is what I like to do, what would happen to this resonant point and how does it move around based on different status of equipment? So you go, okay, I move it, I click, oh, it moved down. It's now at the 6.8. It moved down again. Now it's at 5.9 something. What would happen if I took one of these off? Well, it shifts it back up again. Now, oh, this second resonant point kind of went away. Interesting. When I removed all of the feeder capacitors. And as I move this, you can see it's shifting higher and higher. And now, with no capacitance connected down here, I'm looking at just the upstream. Well, actually, we have these overhead lines, right? And they're adding a little bit of cable charging that's making the impedance characteristic go up. Like it's going to hit a resonant point out here somewhere around the 90th harmonic or something, way far high above the 50th. But if you were to take these out, whoop, that's the power flow. Let me just go and change that. I kind of disconnected everything in the network. So this is a really interesting. Do you remember the result I showed you about the linear impedance as it increases with frequency? There you go. It's here. It's in an actual harmonic simulation. So if I take a scan at this bus and the only thing connected is the transformer and this simple model of the grid, which is again just an R and an X, you're going to see the impedance go up linearly with frequency. All right. What would happen on this bus if there was a grid model? There you go. For the grid model, I'm seeing that for scenario 1, yeah, it's kind of bumping me a little, but it's not really, it's still mostly a linear change in impedance. But what would happen if I would transition to scenario 2? Oh, okay, okay. If this actually does exist and this is an actual system operating condition, I need this. You see what I mean? But remember the catch-22. You don't know if you need it unless you already have it. In other words, you can't see this impact unless you actually had the grid model. Okay, so I'm showing you the impact of the grid up here, when it matters, when it doesn't, And excuse that, that was because I had an isolated system when I was doing that, running the scan. So, okay, we've got a good picture of what's happening up here. We can see the resonant points. Now let's go back. What I'm going to do is go back to this simple short circuit equivalent because it just helps the curves look a bit smoother for the frequency scans. And now let's say, okay, we've seen that the resonant point's moving all over the place. But how is this affecting me in reality? In other words, I haven't simulated any injections from ASDs yet. All I've done is said, cram something into here and show me what the network looks like. We can see there's resonant points, but are they really affecting me? So what we now need to do now is do what's called a distortion calculation. And in Easy Power, you do that by pressing this button, summation. Now, right now, as you notice, I'm going to zoom in here. It's 0 because it's all disconnected. Every breaker is open here to the downstream system. So there's no voltage distortion up here. And when I put on these capacitors, even though this is now changed, and I put one of these on, and there's a resonant point, you'll notice that it's still 0. Even with this resonant condition, it's still 0. There's no injections into the system yet. So now let's start injecting. Let's connect up this feeder. Oh, we're up to 7.98%. Oh, we're up to 7.74% voltage distortion. And of course, we could, if we wanted, we could take these individually offline and see how the distortion changes based on individual harmonic loads being present on the system. So in this case, we're getting a rather high distortion. We're up well over 5%. And there's other combinations. Oh, but look at this one, drops it to 3.7. This one drops it to 2, but if I take this offline, oh, look at this, I'm all the way up to 9.6% distortion down here at this location. So you can see what I'm doing. I'm just changing statuses, and these would be individual cases in your study. You would say, what would happen for this system condition with these 2 banks on and all 3 of these off? One row of your table would have these voltage distortion answers. But that doesn't tell you where the problem is. It just tells you the distortion is high. Well, remember I talked about the bar charts? Even though we know there's a resonance, we know there's a distortion that's high. In fact, let's double click on this bus again. This is the actual distortion condition. Now let's click on the summation that goes along with this. Now let's go to this main bus and look at the bar chart of the voltage. And in this case, what you see is that the distortion is down here predominantly. And let's zoom in on it. Let's say the scale is only 0.2. How about 0.1? So you can see in this case, and this is what I want you to notice. Look at the distortion here, it's high. Where is it high? It's high around here. Where you have the network resonant condition combined with harmonic currents being injected from the grid is where you will amplify the harmonic currents. So you can see that this location, somewhere around the 11th, corresponds to right here. Now, notice at the 11th, it's on the right side of the peak, and the 13th is still amplified a little because it's on the slope over here. It's still on a bit of the amplified slope. Okay, so resonant point transfers to actual distortion amplification, and we see the results displayed as THD right on the one line. And of course, from here, you can do a lot of additional simulations, and I have a few of them shown here in the live example. I have some additional scans. I did a scan with remember all those individual capacitor banks and switching them on and off and the different variations? I just accumulated them here. I just copied and pasted them into Excel and gave them a header, and I just plotted them. So here you have all of those frequency scans, and you can see what happens as different stages. See, this is with C1, C1 plus C2, C1 plus C2 on stage 1, C1, C2, stage 1, stage 2, and then all caps on. So you can see how the resonant point drops as you add capacitance onto the system. Again, that's where it's dropping, but its peak and its amplification factor is remaining fairly high, up around 4 to 5. Finally, in this example, and we just have 10 minutes, and I'll just try to wrap this up here, and then we'll have just a few minutes for questions. 519 compliance. Now, this is the spreadsheet that I put together for myself, and it's very general. In other words, it looks at all harmonic conditions, both integer, non-integer, and odd and even harmonics. And that's why this table looks a little funny. If you were looking at this only from the odd harmonic current perspective and you didn't care about non-integers, then this would be a straight across step down, step down, step down, step down, step down. But because I want this general to cover for many cases for me, this is what I've done. I've created this table so I can copy and paste results in here. I put in my base KV level. I put in my plant maximum load condition. I put in the short circuit strength at the bus, and I calculate this ratio, which then looks up in the table, tells me what table and row I'm in. Okay, so I built the spreadsheet for this example, and you can see some of these numbers. If I were to go to Easy Power, go to Power Flow, solve the case. Well, what did I do wrong? Let's go back out and come back in because I don't remember what switches I had on or off. And if I solve this case, you'll notice that the current flowing into one of these plants at 34.5 is 83.2 amps. You see that right here. And so this was plant B. Did I do plant D? I'm not saying here which one it is, but you can see the 83.2 amps that I put in for the maximum load condition. I would come in here and go to the short circuit analysis and see that the fault duty is around, if I ignore my own self, the fault duty is 3463, and that's the maximum fault current level, 3463, and that generates for the IEEE 519 application this short circuit over load ratio. Again, which tells me which table I'm in the standard in which row. And that creates these limits over here in red. And what I would do for that plant is I would simulate a bar chart, but I have to change it. I have to go to Harmonics, put this back on. I would have to go to the harmonic options. I just know to do this because I've done it 100 times. 0 to the 50th harmonic at a step of 0.125. And then I would do the current at the PCC. I would also have to come to Easy Power, go here and do the from side of the transformer. Here, I would do a bar chart. Once I have the bar chart in amps, I would copy these values right here. See 167.35, I'd copy these and I would paste them into my spreadsheet right here. And from that, then I could compare them. So I've done two plants already for you. I've done plant B and plant D. If you come over here, look at this top table. This is the current distortion in a linear form. You can see that all of the currents are below the harmonic limits. This is a logarithmic form just to kind of zoom in because some of these get down low here and you can't see them. Plant D, however, when I perform the same, I get 64 amps of base load maximum and the fault current's a little higher. I'm in, now I'm in table 2, row 3. In the standard, you can see that the limits have changed and they're a little higher now because you're down into a lower row in the table. But because this plant has a really large 12-pulse drive, you can see that it, in just a couple categories, it is exceeding the harmonic limits of the 519. And over here, you can tell that in the logarithmic form, boy, these are just above, but I would call that compliant because it's very close to where the limits are. But this one is just out of compliance and may necessitate some type of harmonic filtering. Okay, so that is the live example. So let's come back to questions to wrap this up. We have 5 minutes. Okay, does my simulation include any solar banks? I'm sorry, this particular one does not. But to model those, you would need to, solar banks, which include a source inverter, you need to request from the manufacturer a Norton model. So the Norton model has, because they're going to be source inverters, is what they're going to be most likely. So you would want to have the Norton model that has both the harmonic current magnitude and angle, along with R and X at each one of the harmonics, as shown. I think I had a previous example where I showed where that data was. There was a slide here that I went back to. And that would have been under sources. That would have been right here. So on this slide, I'm showing you the typical data that you would get for a Norton equivalent. Amps, angle, R and X, both in ohms. Okay. Are you considering arithmetical summation to calculate total harmonic current at the grid entry point? So total harmonic current at the grid is depending upon how you want to choose to look at it. Okay. I choose, because I'm doing a 519 compliance check, I would choose the basis according to the 519, which is maximum demand current for the plant. And so as you saw in this spreadsheet, what this spreadsheet does is once I enter my current here in amps, these numbers will be divided by the basis, which is IL in the standard. That's and defined as the plant maximum load demand. So everything for the individual harmonics and the current distortion, the ITHD, is calculated according to that. And so we call that in the standard demand distortion, not instead of THD, total harmonics distortion, we call it total demand distortion because it has a basis on your maximum demand. And you can see here for this case that the current distortion turned out to be 8.74% TDD on the basis of 64.6 amps. Okay, any other questions? We base the method on, and we say that the superposition goes so long, the circuits are linear, and then we move to Fourier transform. However, we did not go through the nonlinear elements of the system, such as the magnetization core of the transformer. That is exactly correct. So for a harmonic analysis, we're in the majority of the cases, you're not simulating the third harmonic being produced by the magnetizing of the transformer. We're going to assume that the transformer is a linear element. It's very rare that I've seen third harmonic from transformer magnetizing cause a problem, okay? But if you needed to do that, then you're going to need to up your model, okay? And possibly move to something like PSCAD if you wanted to see how the third harmonic being produced from saturation on a transformer is impacting you. But again, saturation is fairly minimal, right? Because we're supposed to be operating our transformers in a linear location. And then on top of that, the magnetizing current is very, very small. It's like around 1% of the rating. And then the third harmonic that's within the magnetizing current is even smaller than that. So it's going to be no more than, gee, I don't know, 15%, maybe 20% of your magnetizing current magnitude. So that's a very, very small amount of current. And I would think it had very small impact. But you know, it's like I said, when you have a resonance in the wrong place, even small levels of current can be amplified. And so you might have to consider that, yes. Okay, and large solar or wind farm with expansive collector systems, do we need to model harmonic signal cancellation from the various inverters in order to get more realistic current voltage THD values at the POI And if we do, then how do we do it? Okay. It gets really messy because the thing that about these source inverters is the way the harmonics cancel is very randomish, right? If you were to go out and measure, let's say you measured 3 source inverters and got their harmonics and got their angles exactly calculated relative to the driving voltage, which is how you have to get it. You have to get all the angles relative to a single common point of reference, which would be, for instance, phase A on your voltage. With those angles, you could go out and get a sampling of those different source inverters and see how much variation there is in that harmonic content. You could absolutely do that. And I have done that exact same amount of detail on large 36 and 48 pulse rectifiers. I have gone out, I have taken detailed measurements, including phase angle, so that I can simulate what I thought the actual amount of cancellation was going to be from each of the individual harmonics. For worst case simulations, what I typically do is set them all to 0. And then when I get my summed result back at the substation, if I have a measurement that I can compare it to, I'll see how far I'm off. And what I have done in the past is just lower their magnitudes. Instead of simulating the phasing and the cancellation, to be able to get the work done, because as a consultant, you got to get the answer and you can't take forever. And phasing information is kind of nebulous. And it's unknown unless you actually get some data to track it and understand it a little better, maybe statistically figure out where your phasing is sitting at each of your individual harmonics. You got to do something to get your answers. And so I have historically set them mostly to 0 and then dropped magnitudes of the individual sources slightly to then make the result back at the substation appear reasonable. Okay, see, compensation. Regarding harmonic compensation, will the filter be installed near the nonlinear load or at the PCC point? Both or either. It's going to depend on your application and your budget and what you want to accomplish. I like filtering as close to the load as possible as long as it's reasonable. However, if you had 10 sources and all 10 were connected to the same 13.8 kV bus, it would be more cost effective to filter all at the same time at the bus with one filter bank. If you were to filter out at the loads, the actual loads, you would find yourself spending more money. But you would find yourself releasing capacity on the downstream equipment. So let's say the distortion is pretty high and the harmonic content flowing through the upstream transformer is maybe causing some heating. Well, you may want to filter down low because you want to reduce heating in the transformer. And then also you're going to get some power factor correction out of it. And if you get that out of it downstream, you may release some capacity in the transformer that's upstream. So it really depends upon each situation, but yeah, I can see doing it at pretty much anywhere you want as long as it provides the need that you have. It's within your budget. But typically, I would say most of us see medium voltage application of harmonic filters unless there's something really funky going down on the 480 and you need to keep distortion. Let's say distortion is up over 20% or 15%. You may want to filter down low to solve the problem there rather than upstream. Do many EV chargers cause harmonic distortion to the grid? It's all about penetration. How much, right? If you have one EV charging station on a very strong feeder, probably not much, unless the feeder was resonant right in the wrong place. The distortion in harmonics, if you ignore resonance, distortion is strength of grid versus amount of injection. The weaker the grid, the higher the voltage distortion for the same amount of injection. But if you have a medium strength grid, the amount of EV chargers you have online are just going to keep escalating the voltage distortion higher and higher. Okay, just a second. I'm reading another question. And I'm sorry if I didn't get these in order. And a harmonic analysis superposition rule so that we say, so long circuits, applicable, so the long circuits, unlinear. Oh yeah, I discussed that one already about the magnetizing the transformer. So I think I've hit all the questions that are on here.
Excellent. Well, thank you so much, Chris. And also, just to remind everyone, I will put my email here in the chat once again in case it's gotten buried. But if you haven't gotten your question answered or you think of one at a later date, please do send me your question and I will make sure it gets answered. Oh, it looks like maybe one more popped up, Chris. While modeling solar inverters, is it necessary to request harmonic data before the inverter internal AC filter to evaluate the frequency scan at the POI with the inverter filter?
Okay, while modeling solar inverters, is it necessary to request for harmonic data before the inverter? In just a second, before the inverter internal AC filter evaluate the frequency scan at POI? Okay, this is an interesting question, and this is depending on whether you're saying filter as in a choke, just a reactor, or if you're talking about a real filter connected onto the AC. As I noted earlier, every time anything capacitive is connected on the AC side, it has to be included. So I would say that if the filter is like a notch filter or something that includes inductance, capacitance, and resistance, you would want to model that as a separate component, and you would want the injection coming from before the filter, okay, so that you're modeling that correctly in your AC network. Because let's say there's a lot of them, they can possibly accumulate, if you have many of these inverters tied in parallel or at different locations around the system, and they're accumulating. So yes, I would definitely model it. If it's on the AC side, then yes. If it's on the other side of the DC bus, no. But if it's on the AC side, absolutely, I would include it. But however, I would note, some manufacturers will include the current injection and that filter and their smoothing reactor from their inverter bus to the AC bus. They'll include all of that in the Norton equivalent. So I would suggest that method first. Ask for the complete Norton equivalent looking, from the very exterior with all the internal, whatever they have inside. Get that Norton model at that connection point, the point of connection. And that should be a complete representation of everything behind it. Thank you. I appreciate everyone being on and hanging on for 3 hours. I know it's a long period of time, but thank you so much for attending.
Thanks, everyone. And again, if you have any questions, just please let me know. The recording will be made available probably by the end of the week, if not early next week. And thank you guys for joining us. That'll be it.
All right. Take care, everyone.
Thanks, Chris. Bye-bye.
Bye.